This is the second packet for our final review. We're doing multiple choice units 6 through 1, and then by the end of this packet we'll be all done for the review unless you need to keep studying your speed sheet. Number 1, we have a definite integral between 1 and 2. So the first question that I always think of when I see an integral is, do I need to pay the tax person? And in this case, no, because we don't really have a house. Notice that over here, this is just an empty set of parentheses. There's no power up here, like power of 2 or something. So it's each individual piece that's going to be taking the antiderivative. Moving forward, that's going to turn that into a 4x to the power of, it goes up a power of 4, divide down by that 4, and then subtract. Now let's deal with that 6x. Antiderivative will go up to the power of 2, divide down by the 2, and we have it. And then this is going to be evaluation bar between 1 and 2. And now that we have this, we're going to plug these numbers in. I'm going to do some cancellation first. I'm going to say that this is really x to the power of 4 minus 3x squared evaluation bar between 1 and 2. That'll make my life a little bit easier. And then from here, that's going to be 2 to the power of 4 minus 3 times 2 to the power of 2. That's the first half, which I'll put in parentheses. And then I'm going to subtract the second half. Subtract. Now if I plug in 1 in here, I'm going to have, it's a little bit hard to write on the right side of the iPad here, but it's going to be 1 to the power of 4 minus 3 times 1 squared. And I can simplify this now. That's going to be, so 2 to the power of 4 is 16. Minus, okay, first I'm going to be doing 2 squared, which is going to be 4, and then 4 times 3 is 12. So it's going to be minus 12. That's still inside parentheses. And then we are going to subtract. Again, all of this should really be in parentheses. Man, I cannot. So I'm trying to write it so that my hand is not touching the iPad, which is a little bit harder than I thought. There do need to be a set of parentheses there so I distribute the negative correctly. So there's that set of parentheses again. That's going to be 1 to the power of 4 is 1, 1 squared is 1, times 3 is 3, so 1 minus 3. And this is going to be 4 minus a negative 2, which is going to be 6. And hopefully that's an answer. Yes, all right, we got it. C. Number 2. No definite integral, so that means we're going to have a plus c, and all these options have that plus c, so we don't have to remember to do that. You'll notice that you can't really, there's no such thing as anti-powerhouse, or like if you pay tax person, it won't work for this problem. So the only way to attack this problem is to take this square and actually square that that inside. So whenever you have a binomial square, there is a shortcut. It's to square the first, double the product, and square the last. And I can write that here. The shortcut is to square the first, double the product, and square the last. Or I should say square the second. But maybe you don't like that shortcut. I know that for this year I have 2 or 3 students that just don't remember this one. So if you don't remember this, there's the long way to do it too, which I'll be showing here. And that's going to be using a unit, or not a unit square, but a general rectangle. If I hold that, it should turn into a nice rectangle. Thank you. There should be a straight line there, straight line right there. And I'm just going to put the sides of this rectangle as x to the power of 3 plus 1 and x to the power of 3 plus 1, because I just need to multiply x to the power of 3 plus 1 twice. And let's do it. So x to the power of 3 times x to the power of 3 for this cell right here is going to be x to the power of 6. This is going to be x to the power of 3, x to the power of 3, and this is going to be 1. Adding up all of that area leaves us with x to the power of 6 plus 2x to the power of 3 plus 1, and you'll see that the shortcut did work, because if we square the first, that's this thing squared, which is x to the power of 6. If we double the product, we need to first find the product. The product of 1 times x to the power of 3 is just x to the power of 3. Doubling x to the power of 3 gives us 2x to the power of 3. And squaring last, squaring 1 means I have 1. So shortcut did work, but there's a long way as well. And now we're ready to take the antiderivative. So that was just all the preparation work. So now we need to do the antiderivative of x to the power of 6 plus 2x to the power of 3 plus 1. And again, you always have to ask yourself tax person whenever you're going backwards, but there's no tax person in this case because there's not really a giant house that we have to worry about. So it's strictly going to go x to the power of 7, it goes up a power, divide down by that power, plus 2x to the power of, it goes up to the power of 4, then divide down by that 4, then finally plus x. It was 1x to the power of 0. This is the way that I think about it, right? X to the power of 0, and it goes up a power and then turns into x to the power of 1, divide down by 1, and it's still 1, x. And don't forget your plus c, but I mean, it's a multiple. What? Whoa. I don't know what just happened there. It went back to the previous problem, I guess. I don't know how. Okay. Whoa, check that out. It's interesting. Don't forget your plus c. Plus c. Is there anything that matches that? I see b. B matches it pretty darn closely, right? Just double checking. Yeah, that looks good. Moving forward to number 3, another definite integral, and I have a fraction, which is annoying. I can rewrite that fraction. I can say that it's equal to this integral between 1 and 3 of x times x squared plus 1 to the power of negative 1 dx. Will that help me? Maybe. I think it will. This has to be tax person, right? Because there's just too much going on here. So I'm going to choose the most complicated thing. I have really two choices. Whenever I see multiplication, I can either choose this or I can choose this. And I'm choosing this to be my most complicated thing, and I think you'll agree with me. So that means my house is going to be a power house. You can probably already see it's going to be a natural log house, just judging by the answers that we have down here. So I'm going to say that my inside of the house is x squared plus 1. The tax person, knocking on the front door this time, is going to be x, and then my u prime is going to be 2x. And check that out. When I turn this into a fraction to pay the tax person, the x and x will cancel each other out, and this is left with 1/2. So paying the tax person means that we have the integral now from 1 to 3. X turns into 1/2, and I still have this x squared plus 1 to the power of negative 1 dx. And I will purposely fall into the trap that most students will do on the first time that they've seen this, if they haven't seen it before, where you say, okay, well, I'm ready to take the antiderivative. So this is going to be 1/2 x squared plus 1 to the power of, okay, it goes up a power to 0, and then I divide down by 0. Oh, wait a sec, that doesn't work, and that's because you can't divide by 0, and there is a special rule for this one. The special rule is whenever you have anything to the power of negative 1, that anything, the antiderivative of that anything is going to be a natural log. So this is going to be 1/2 natural log of absolute value x squared plus 1 and absolute value, and don't forget our evaluation bar between 1 and 3. And the absolute value is kind of unnecessary here, and that's because x squared is always positive, and if I add something to a positive, it's always positive, so I can kind of drop the absolute value symbol if I want. And I can write an equal to sign so people can follow the work here. And then when I move down and evaluate this thing, I'm going to have 1/2 natural log of, and I'm going to drop the absolute value now. I'm going to first plug in 3. So I have 3 squared plus 1. And whenever you have a constant term like this 1/2, you can kind of factor it out. So the way that I'm thinking about this is 1/2, excuse me, is being factored out of this entire problem with the evaluation bar. So just like that, I'm going to go ahead and say 1/2 is being factored out, so I don't have to keep rewriting it again. And then I have the next piece of this where I subtract natural log of when I plug in 1. So when I plug in 1, I'm going to have 1 squared minus 1. And now that's an issue because, oh, it's plus. I was like, why do I have a minus? That's undefined. There we go. and this is now going to be equal to 1/2 times the quantity of natural log of 3 squared is 9, 9 plus 1 is 10, natural log of 10 minus natural log of 2. And now I'm starting to look for answers, and that isn't an answer, which is unfortunate, and I see what they're doing now. They're trying to simplify this. So whenever you have two natural logs subtracting, you're really dividing the insides, and it's coming from this old rule from Algebra 2 or Pre-Calculus. I think it's first taught in Algebra 2 and reviewed in Pre-Calculus, that if I have log of any base x of some number, I'll call it a, and I add log of that same base x with some other number, that's the same thing as doing, oh, and I ran out of room, so I'm going to drag you to the left here. That's the same thing as doing log of that same base x of a times b. That's one of the rules that you should remember, but the other rule is kind of the same thing, but the reverse, where if I have log base x of a minus log base x of b, then I'm going to divide the insides. This can be log base x of a divided by b for the insides. So I'm using this second property right here for our problem because I have subtraction. I guess the x in our case is base e, right? Because natural log is base e, and just divide the insides. So I can say that this is equal to, I want to go back to blue though. So this is going to be equal to 1/2 natural log of 10 divided by 2, which is 5. And is that an answer? 1/2 natural log of 5. For problem number 4, we're trying to find if it's continuous at x equals 2, what is the value of k? And this is using the continuity test, and the continuity test essentially just says make sure that the left is equal to the right, which is equal to the actual height. And notice that the left and the height are the same point, because wherever the height is, wherever this height is, wherever you have an equal to sign, which is that equal to sign on the inequality. So essentially just say this is equal to this, and then plug in x is equal to 2, and see what you get out. So I'm going to say x squared minus 3x plus 9 is set equal to kx plus 1, and plug in our suspect point. Our suspect point is 2. So now I have the quantity of 2 squared minus 3 times 2 plus 9 is equal to, and then it really should be k times 2. I'm going to say 2k though, 2k plus 1, and solve for k. And clearly we're going to get an answer, so the answer is not e. It's going to be 4 minus 6 plus 9 is equal to 2k plus 1. 4 minus 6 is -2. -2 plus 9 is 7, so 7 is equal to 2k plus 1. Subtract 1 on both sides, so 6 is equal to 2k. Divide by 2 on both sides, k is equal to 3. And that means our answer is C. Moving on to number 5. So the first thing that pops out to be in number 5, it's the limit to infinity, and that always is a speechy definition. Whenever you have the limit as any number, it could be x or k or n. I'm going to just do x in our, I think x is on the speechy. As x goes to infinity, this is the definition of a horizontal asymptote. There's a silent P in there. And a horizontal asymptote, to find that, you're going to have to use your top-bottom rules. So notice here that the top-bottom rules basically state, look at the power, the highest power. The highest power up here is a 2. The highest power down here is a 2. So if the top had a bigger power, then the answer would be infinity. If the bottom had a bigger power, the answer would be 0. But because they match, it's going to be a magic fraction. And the magic fraction says ignore everything else, and then you just take the coefficients, 4 for the top, and I guess 1 here for the bottom, and the answer is going to be those coefficients 4 over 1, and the answer is just 4. Moving on to number 6. All right, we've got this graph, and we're looking for something that is true. And it's always important to underline true, because sometimes they're asking for what is false, and if you misread the problem, you will definitely get the wrong answer. All right, so that means all of these things essentially are false except for 1. So when I see A, I notice that x is going to 3, but I view that as from the left and the right. This is the double-sided limit right here because there's no plus sign or minus sign after the 3. So double-sided limit from the left and the right must approach a height of 1. So as x approaches 3, so x approaches 3, the left seems to be approaching this height of 3. Which is already wrong. So I can immediately eliminate A, but look from the right side as well. From the right side, it seems to approach this height of 3. We don't care what happens at this point. Usually what I tell students is to draw a line through that point. Anything on that line, I do not care about. Like cross off everything on this line. So that means ignore this point, ignore that point. What does it seem to approach? It seems to approach a height of 3. It seems to approach a height of 3. So if they had written a height of 3 right here, then that would have been correct, but they did not. So this one is false. I'll put a little F here and cross that off. That is false. What about part B? So part B is also a double-sided limit because it's just 4 with no plus or minus sign. So let's take a look at 4. So again, I'm kind of drawing a line through 4. And I don't care what happens at those points. I just care what happens as I approach that point. So as I approach 4, I seem to be approaching a height of, I don't know, 1.5, and then that's from the left, and as I approach 4 from the right, I seem to approach a height of 3, which is okay for the right-hand side, but the left-hand side is not the same as the right-hand side, which means the actual answer here should have been D and E, but they wrote 3, which is not true, so that's false. Part C, f of x is continuous at x equals 3. Okay, so this is time to remember, what does it mean to be continuous? So your speed sheet definition for continuous, I don't even know if we have a speed sheet definition for continuous. There's discontinuities. The definition of continuity or something is continuous is it does not have things that make discontinuities. And those are the 4 things. So I should say it doesn't have one of the following things. You have, I don't know, I'm doing bullet points and that. So I'm going to say holes, gaps, VAs, I kind of want to make that a capital VA, VAs, and endpoints. So let's go ahead and look at x is equal to 3. So at x is equal to 3u, do we have a hole, gap, or anything? And we do. We have this giant gap. Or you can think of it as a hole and a gap, kind of, right? So there's a hole there, and then it jumps down here. I would classify that technically as a hole, but it doesn't matter. It is a discontinuity here, so it is not continuous. So that one is false. Remember that we have an easier definition of continuity, and I'll write that down for us as well. I'll say, or don't pick up your pencil. If you don't pick up your pencil, then you're continuous. And look, if we had to do that, I had to go over here, pick up my pencil, go here, and then pick up my pencil again and come back up here. So I had to pick up my pencil, therefore we're not continuous. Okay, eventually one of these is going to be true, right? I'm hoping. So f of x is continuous at x equals 5. So again, x equals 5 is right here. So at this point right here, it's asking. And let's just use that pick up the pencil definition. Did I have to pick up my pencil to go like that? No, it is continuous. I mean, it's a sharp corner, which is not differentiable, but it's not asking about differentiability. It's only asking about continuity, and I didn't have to pick up my pencil. It did not have a hole, gap, VA, or an endpoint at this spot. And you might be thinking, well, that's an endpoint because it's a point, right? Well, it didn't end. It kept on going on, right? So we finally have our first true answer. So that is true, and that is the correct answer. And I'm not going to stop there. I want to go ahead and analyze E to show you why that one has to be false. So by process of elimination, it has to be false, but why? So when I'm reading this thing, the limit as x approaches 6, that is, I read that from both sides. So as x approaches 6, ignore that point on the line. On the right-hand side, it seems to be approaching a height of 1, and on the left-hand side, it seems to be approaching a height of 4. And those don't match. So the answer here is, on the left-hand side, should have been does not exist. And f of 6, so the way that I interpret f of 6 is the height at 6, or the y-coordinate at 6. So at 6, where does this line actually touch? This line actually touches this point. It doesn't touch this point because that's an empty point, right? It does touch this point. So the height here is actually at 1. So f of 6 is exactly equal to 1. And now does d and e equal 1? Well, obviously no. So that one's crossed off. On to part number 7, or question number 7. All right, so if x approaches 3 from both sides, again, whenever you have no plus and no minus after this, you assume that it is from both sides. So from both sides, we get a height of 7. Which of the following must be true? And I'm going to underline this word true because sometimes it asks which of the following must be false, right? Number 1 is saying f is continuous at x equals 3. Okay, and it's using this word continuous. So we need to go ahead and remind ourselves. I'm going to use that easy definition of continuity. Don't pick up your pencil. And I already wrote that down up above, so I'm not going to write it down again. We haven't defined differentiable, so let me define what it means to be not differentiable. So not differentiable means that you have one of these things. If you're not differentiable, that means you have a sharp corner. That's supposed to be an R right there. You have a horizontal tangent. So I'll say, wait, did I say horizontal tangent? Vertical tangent. I apologize. Vertical tangent. And I think that everyone knows what a sharp corner looks like. Like that's a sharp corner, right? But a vertical tangent, and that's a little bit harder to visualize. You don't see that as often. That's something where you have a function that comes up straight and then keeps on going. And at this spot right here, if I were to draw a tangent line, the tangent line would go straight up and down. That would be a vertical tangent. And then finally, it's not differentiable if you have any discontinuities. Discontinuities. And what are discontinuities? It's everything that I just lifted up here. So it's really these 4 plus these 2 make up things that are not differentiable. So it's a lot of things. It takes a lot to be differentiable. And then finally, the way that I'm interpreting this is the height at 3 is equal to 7. All right, so to solve this one, the easiest way to do it is to play devil's advocate and draw a graph where you try to make as many of these things false as possible while still holding true to the original condition. So here's my graph for my devil's advocate. What if I had some graph here? Thank you for making straight lines. Love technology. What if I had some graph where here at x is equal to 7, I have x is equal to 3. I don't know why I did 7. X is equal to 3, and this is now no longer to scale. So what if I go like this? I'll say here is 3, here is 7. I know that from the left I should be approaching this height of 7. So I don't know, I'm going to come from the left, and I'm going to approach this height of 7, and then I'm just going to have a hole, and then it continues on. There's my graph. If I had this as my graph, my initial condition is still true because as I approach this point from the left, I get a height of 7. As I approach this point from the right, I get a height of 7. So this condition is true. So am I continuous? And the answer is no. I had to come up here, pick up my pencil, and then continue on. If you pick up the pencil, it cannot be continuous. So I can go ahead and say, nope, not you. Is it differentiable? Well, I just told you that it's not continuous because we had to pick up our pencil. If it's any sort of discontinuity, then it's not differentiable, and it's claiming here that it is differentiable, which is false. It is not. We had to pick up our pencil. It can't even be continuous, let alone differentiable. And then finally, it's saying that the height, I wanted to be in laser pointer mode there, but it's saying that the height here at 3 is 7. Well, the height here at 3 is, there is no height. I mean, you have to draw a line through 3 and then it intersects it where? If I had maybe a point up here, like, I don't know, there's a point right here, and then I drew my line, I say, okay, well, yes, the height here is actually 3 or whatever, whatever this y coordinate is over here. But there isn't even a point here. So there's nothing. There is no height. It's undefined. So that one is also not true. None of these are true. The correct answer here is A. None of them have to be. And for problem number 8, we have a cool little function up here, and we're looking for a value of x that is continuous but not differentiable. So it's 2 things. It has to be, yes, it has to be continuous. It has to not be differentiable. So the first thing that I see is, okay, let's go through all these in order. The old definition of continuity is don't pick up your pencil, right? So if I'm coming here, did I pick up my pencil to do that sharp corner? No. So this point right here is continuous, and it also helps to have the definition of not differentiable. So if something is not differentiable, if you have one of the following things, you have a sharp corner, or you have a vertical tangent. and if you have any sort of discontinuity. And there are 4 different types of discontinuity, so that's kind of a long list, but just generally speaking, if you pick up your pencil, you cannot be differentiable. So the correct answer here is already A, because look, we didn't pick up our pencil, so it's continuous. Check that one off. And it's a sharp corner. It's that first thing, which is not differentiable. So that's the answer. But let's go through all of these to make sure that you understand them. So when I get to B, I had to pick up my pencil, come up here, and then continue down here. So I had to pick up my pencil, so it was not continuous. It's also not differentiable because it's not continuous, right? If I come back over here, I had a gap. I had to pick up my pencil and come back over here. So if I ever pick up my pencil, it can't be continuous. And then when I come out over here at E, I don't have to pick up my pencil. So it is continuous, but the problem is I don't have one of these 3 things at E. I don't have a sharp corner or vertical tangent. So this one is differentiable and continuous, but we're looking for something that was not differentiable. Problem number 9. If x is continuous on the closed interval, which the following statements are not necessarily true. Okay, so I'm going to underline not true. And man, if I don't have technology to make a straight line, I'm kind of at a loss, aren't I? Technology, thank you. All right. So the first thing that I'm thinking here are my theorems, my IVT, EVT, and MVT, because I'm hearing the words closed, continuous. These are conditions that are necessary for our theorems. Let me remind you what those theorems are. So with IVT, EVT, and MVT, IVT, there are the things that every theorem needs and the thing that they prove. And I think I did this summary on 1-9 or something. It was in our first unit and I did a good little review, but here it is again. IVT needs to be continuous, and if it is continuous, then it proves heights. EVT needs 2 things. It needs to be continuous and it needs to be closed. And if those 2 things are met, then it proves max and mins. It only proves that they exist. It doesn't prove where they are. And MVT only needs 1 thing. It needs to be differentiable. And by the way, if you're differentiable, then you are automatically continuous as well. So some people think, oh, you need 2 things. It needs to be continuous and differentiable. But no, differentiable means that you are already continuous. So you really only need to be differentiable. And if you're differentiable, then it proves slopes. So there's my cool little table. I guess I could have made that first line straight. All right, so what do we have here? What are the needs that are met? So I see the word continuous, so I'm going to box that one. And I see the word closed. Do I see the word differentiable anywhere? No. All right, well, because I don't have the word differentiable, I cannot use mean value theorem because differentiable has not been met. So anything that is talking about slopes, and hey, check it out, right down here, it's saying f prime of c. That is a slope. There's no way to prove this because we're not differentiable. I have to cross this one off. So cross off 3. That one, wait a sec. We're choosing something that is not necessarily true. I was going backwards, so I have to be really careful here. I would say that 3, that one is not necessarily true because MVT has not been guaranteed. And what about 1 and 2? Well, 1 and 2 are using EVT because they're both asking for a minimum and maximum, which are proved with EVT. And remember, EVT just says there is a minimum, and that's what this is saying. There is a minimum, there is a maximum, which are guaranteed because we met the conditions for EVT, and therefore EVT applies. So these ones are true. These have to be true. This one has to be true. 3 is the only thing that might not be true because we never... well, there's 2 reasons. First of all, we never said that it was differentiable. But second of all, even if it did say we were differentiable, we don't necessarily know that it's going to be equal to a specific number because it didn't give us any numbers in the problem. So there's 2 reasons why 3 are not true. So the correct answer here is just C. Moving on to number 9. All right, we got a table. And okay, I'm seeing these words continuous and differentiable, so I'm automatically, again, thinking of our IVT, EVT, and MVT theorems. So I'm seeing the word continuous, and I see the word differentiable. Okay, so continuous unlocks IVT, differentiable unlocks MVT, and closed, okay, we've unlocked all the theorems. We can use any one that we want. Table gives selected values. Which of the following statements must be true? Okay, so we're doing true this time instead of not true. It's saying that the minimum value is 12. And you have to be careful about this one because Whenever you're claiming there is a minimum value, you're correct. But whenever you claim that there is a minimum value and you know what that value is, that is never going to be true, ever. So that's not true. You'd think, oh, but EVT applies to this one because it's closed and continuous, and therefore we can guarantee a minimum. We can't guarantee exactly what it is. And even though it looks like 12 is the lowest value on the table, what if there was a hidden value here at 4.5 and it was like 10 or something? You don't know that. This table is incomplete. So maybe the minimum value is smaller than 12. We have to say, no, that one could potentially be false. Part 2, there exists a C such that f prime of C is equal to 0. Okay, so this one could be true, but we have to do a little bit of math. So the first thing I'm seeing is f prime of C. The way that I interpret f prime is slope, and C is just some point, because there's some point between 3 and 7. Between 3 and 7, there's some x value in this range where I get the slope that is equal to 0. So the thing that guarantees slope equal to 0 is MVT, and the definition of MVT is that f prime of C is equal to f of B minus f of A all over B minus A. And we want f prime of C to be 0, so I'm going to say that f prime of C is 0. So if I do that, I'm going to say 0 is equal to f of B minus f of A all over B minus A. Then I can do some cool little tricks here. I can multiply both sides here by B minus A, multiply on this side, multiply B minus A on this side. By the way, I'm doing way too much work. There is a shortcut, and I'll show you that at the very end. These cancel out. 0 times anything is still 0, so it's as if that B of minus A never existed. I now have 0. I want to go back to blue, though. And I want to say that 0 is equal to f of B minus f of A. Finally, add f of A to both sides, and f of A is equal to f of B. If this condition is met, then it is true that f prime of C is equal to 0 somewhere between 3 and 7. So can you find a y-coordinate and f, like anything in this column where they match, where f of A and f of B are the same? I double hit the iPad there, sorry. There's no double of 17, no double of 12, no double of 16, but there is a double of 20, and because of that, this is indeed true. So I can come down here and say, you don't have to say this, but like this sometimes is asked in a free response question, so you should get used to this. This is true. Why? Because f of 3 is equal to f of 7. So this is indeed true. So I'll circle that one. And for number 3, f prime of x. That means, so okay, you have to be careful here. You might think that f prime of c and f prime of x are saying the same thing, and well, clearly one is a c and one is an x, but there is a slight distinction. C just means some point. There's one point in between 3 and 7. But f of x means all points. This is saying all slopes. That's how I'm interpreting this, and I should probably write that down because it's important. This is saying all slopes are greater than 0. And that's saying between 5 and 7. Okay, well, let's take a look at the table and show you why this is a tricky question. So between 5 and 7, it seems that it goes up. 12 goes up to 16, up to 12, and if you're going up, you need to have a positive slope, and this is saying the slopes are positive. But again, that is misleading because we have incomplete data. What if, I love playing the what if game, what if I had a value at, I don't know, 5.5, where instead of going continuously up and up, 5.5 is right here, right? What if I went from 12 to 11? If that value was added to the table, then it would not be true anymore because I would go from 12 to 11 and then from 11 to 16 and then from 16 to 20. But I've gone down. I might still have a negative slope. So because we have incomplete data, we don't know all slopes. We know in general, it seems to agree with that, but we can't prove that. It doesn't have to must be a true. So this one is potentially false because it's incomplete data. So it's not 3, it's just 2, it's just B. All right, and on to number 11. And this one, I immediately see that we have x going to infinity, which means two things always for our speech sheet definition. The first thing is that this is trying to talk about a horizontal tangent. a line that you approach when you go to negative or positive infinity. And second of all, in order to find the value of that horizontal tangent, you have to use your top-bottom rules. That is, again, supposed to be an R. All right, so the problem here is that they haven't multiplied everything together, so we need to do that. And you need to be careful here, and there is a shortcut as well. By the way, I think I mentioned in the last case, you didn't have to do all this work. As long as you can find two values that are the same, you get 0. That was the shortcut. The shortcut here is we don't care about this -1. We don't care about this 3 because we only care about the highest power. We really need to only multiply the 2x with this negative x. This negative is still included here, and that is going to be a purposeful trick that the AP test is trying to throw at you. If I just multiply the highest degree terms, I should get the highest degree term out of that. Same thing down here. You can kind of ignore the -1 and the +3 and just multiply together the x and the x. So the way that I would write this is still equal to the limit as x approaches infinity, and then 2x times negative x is a negative 2x squared, and I'm going to say plus ... something else that I don't care about, a lower degree term. And because I'm bad at drawing straight lines, I'm going to have technology help me. Thank you. All right, and then I multiply x times x, and I get x squared plus ... some other lower degree term. All right, now I'm going to use the top-bottom rules on this function that I've created. And top-bottom rules state that, hey, if I have the same power, then I'm going to have a magic fraction. Magic fraction says, hey, look at your coefficients. I have a -2 on the top and a 1 on the bottom, and you divide those, and you say, okay, well, the answer is going to be -2 over 1, which is just -2. So the correct answer here. Number 12. We have a function f, not f prime or anything, up above, and we're looking for statements that are true. All right. So, so I'm looking at all three of these statements. I'm noticing they're basically all saying the same thing. One of them is asking what's going on from the left, what's going on from the right, and then the double-sided limit. But they're all happening at 2. So let's look at here. So at 2, from the left-hand side, I seem to be approaching some height. I don't know what height that is, but it is a height. Therefore, the left side does exist. So I can say that that's true. It does approach some height. Exists just means that there is a height, right? And as I approach it from the right-hand side, plus means from the positive side. So from the positive side, I seem to approach some height. It's whatever that height is right there. So that one is also true. In order for this last one to be true, the left and the right height have to be approaching the same height. And you'll notice that is not true. This seems to be approaching this height versus this height. These two heights are not the same. Whenever they're not the same, it's false. The double-sided limit does not exist. So it's just 1 and 2 only. So I can circle those 1 and 2 only. So the correct answer here is C. Number 13, we have this piecewise function, and it's asking for the limit as x approaches 2. And again, we don't have a plus or minus, so that's the double-sided limit, just like we had up here at the double-sided limit. So all we're going to do here is we're going to plug into the left, plug in the right, and if the left and the right equal each other, then we're going to, like, maybe the left and right are equal to natural log of 8, then the answer is natural log of 8. If the left and the right do not equal each other, then it's non-existent. It's going to be E. So we're going to rewrite this natural log, but instead of x, we're going to plug in the suspect point. The suspect point is the halfway in between point, so it's fine, it's fine. Oh, it breaks at 2 and then continues at 2, so 2 is going to be our suspect point. We don't know if that point is going to be continuous or not. So natural log of 2, and that's all we can do. Okay, that was the left piece. And for the right piece, we have x squared natural log of 2, so x squared is going to turn into 2 squared natural log of 2. I believe that looks good. And you can see that's going to turn into 4 natural log of 2, and 4 natural log of 2 is not the same as natural log of 2, and that was the right piece. Because the left and the right do not equal each other, I'll go ahead and put not equal to each other, the answer here is non-existent, E. Number 14. All right, so I've got some keywords. I'm going to kind of box things that I care about. It's continuous. That's going to be helpful if I ever need to use intermediate value theorem or anything like that. Defined in all real numbers. Okay, it gives us a height. So it says, okay, at x coordinate -5, we have a height of 3 or a y coordinate of 3. And at x coordinate -1, we have a height or a y coordinate of -2. And if we have a height of 0, this is saying for only 1 and 1 value. So at one x coordinate, we have a height of 0. Then which of the following could be x? Okay, so when do we have a height of 0 is asking. Do we have a height of 0 at -7, -2, 0, 1, or 2? I mean, it's only one of those. So what's really happening here? And I was correct in my analysis. Like whenever I see that keyword continuous, I am by default thinking of my IVT, MVT, EVT, all of those. This is IVT. This is asking about heights because it asks for, this is a height of 0. So IVT guarantees heights. I'm going to go ahead and draw out a bit better what's going on. And I'm just trying to think. So I have, in terms of drawing my axes, I go from -1 to -5, 3. So everything is negative. So here's what's happening. I have, I want to go to my actual pen now. I have my y-axis and I have my x-axis. Wow, that was, okay, it does think that's a line. Thank you, technology. So at -5, I'm going to put like a -5 right here. I have a height of 3. I'm going to just using this information and making it into a point. So I have -5, -5. I have a height of 3. A height of 3, I'm going to randomly say is, I don't know, right there. So I'm going to say I have a point right there. That's all I know from the first bit of information. And then the second bit of information, I have another point at -1, 2. So at -1, I'm going to say is right there. And then comma -2, which I'm going to say is right there. It's -2. I guess I should have had the height up here of 3. And I have a point right there. That's all I know. The way the intermediate value theorem works is you basically make a rectangle with those 2 points. So here's my rectangle, my attempt at a rectangle. Oh man, you can see that I'm gonna need technology to correct that into a rectangle, please. Did I pick up I guess I picked up my pencil somewhere. Yep, there I did. Okay, try this again. Okay, hold down. What? I swear to God, I'm not picking up my pencil. I guess I picked it up multiple times. I don't know why it thinks that. Maybe I have to go faster. Okay, I went pretty fast there. There we go. Everything inside of that rectangle, all the heights in that rectangle are guaranteed as long as we are between -5 and -1. Every height in that rectangle is hit between -5 and -1. All right, so notice that -7 is out here. Nothing is guaranteed. It's not inside the rectangle. -2 is guaranteed. -2 is right here. We do have a height of 0. And by the way, it is important to note that 0 does happen inside of a rectangle. If it was like, where do you have a height of 5? And it's like up here. Well, it's not even inside the rectangle. Luckily, 0 is inside the rectangle. So we are asking the correct question. -2 is in this rectangle, so that works. 0 is right here, not in the rectangle. 1 is right here, not inside the rectangle. 2 is right here, not inside the rectangle. There's only one value that was inside of the rectangle. The correct answer here is -2, or B, and I want to draw that in blue. So the correct answer was B because -2 was the only value that is inside of our I don't know if there's a name for this. I'll call it the IVT rectangle. All right, number 15. All right, so we're plugging in a number. If the number works, we're done, right? So let's just plug in 0. And right away, you'll see pretty quickly, that's going to be 0, that's going to be 0, that's going to be 0, that's going to be 0. When we plug in, that should always be your first idea. If you plug in, you get 0 over 0, which is called the indeterminate form. Whenever that happens, you're going to do the following 3 things. You're going to factor, you're going to cancel, and you are going to plug in again. Oh, that's not how you spell plug in, Mr. Sindel. Plug in. All right, so factor comes first, and I see that the greatest common factor is, okay, yes, you could factor out a 2, but I noticed that the bottom isn't going to be factored out at all, so I'm not going to factor out the 2. I'm seeing that I'm seeing into the future. The only thing that's going to be canceled out in this cancel outs phase is this x to the power of 3, so I'm not going to factor out the 2, but you can, you'll still get the same answer. So I'm going to get an x to the power of 3 factored out. That leaves me with a 2x to the power of 3 plus 6. And for the denominator, I'm going to factor out another x to the power of 3, leaving me with 4x to the power of 2 plus 3. I don't know why I had a brain fart there. And So I did step one. I can go ahead and be like, yep, check, I did factor. Now I'm on to cancel. So is there anything that I can cancel out? And indeed, this x to the power of 3, x to the power of 3, those are gone. So I can give myself a check for cancel. And then finally, plug in again. What am I plugging in? I'm plugging in 0 again. So plug in 0. If I plug in x is equal to 0, this x and this x are both zeros, which means this term are both zeros, leaving me with just 6 over 3. So this is going to... I mean, I have to be careful. Mathematically, this is not technically correct because I should have a limit out in front of this to make this an equal to sign. But I'm going to be lazy. I'm going to say, yeah, if I take the limit, I get 6 over 3, and that's equal to 2. The correct answer here, whoa, don't know what happened there, is D, 2. Number 16. All right, I have limit with a bunch of h's. Usually when that happens, you're going to be doing some sort of the definition of the derivative. And to us, that just means we're using our tool called the hot box. We're going to say, okay, everything inside of that box we care about. Everything that is not inside that box, we don't care about. We're stuffing it all right here. Okay, so hot box rules, we say, what is being added to h? Well, 2 is being added to h. So that means our value of c is 2, the thing being added to h. Once you know the value that you're evaluating at, 2, then you can cross off everything with that h and change that into an x. This whole thing is just x, which means that is our function. Our function, our f of x, the function that we're talking about is just e to the power of x. And you can kind of see e to the power of x right there. And then this is the definition of the derivative, which means you need to therefore take the derivative. So if I have f of x is equal to e to the x, what is f prime of x? What is the derivative of e to the x? And luckily this is an e-house. E-house is the easiest out of everything. It's just e-house again, and then you have to multiply by dinner. Never forget your dinner. E to the power of x. And the derivative of x, the dinner, is 1. So you could multiply by 1 here, but that's kind of silly. I'm just going to leave that as e to the x. And then finally, we have to plug in our value of c. What is f prime of c? Well, that's going to be e to the power of u. So I should say f prime of 2, right? E to the power of 2. And there it is. Correct answer, D. Number 17. We have our function, and we want to first take the derivative of the function and then plug in -1. So taking the derivative, I'll write that over here, f prime of x is going to be equal to derivative. This 3 is going to come down in front, and I'm going to have -3x, and then it goes down a power from 3 to 2, plus, okay, x, that 1 comes down in front, and then it goes down to just 1, and then 1 over x. So again, the way that I'm going to do this is I'm going to rewrite 1 over x as x to the power of -1, and the -1 is going to come down in front, so I'm going to say -1 x to the power of, and then it's going to go down a power. It was already at a power of -1, and it's going to go down even further to -2. So it's going to be -2. So there's my derivative, and I need to plug in -1. But before I do that, I kind of want to rewrite this term right here. Really, this is just -1 over x squared. I flipped it because whenever you have a negative power, that just means turn it into a fraction, make it in the denominator, right? So now I can plug in. I can say, okay, I'm going to plug in that -1, and I get f prime of -1 is equal to -3 times -1 quantity squared plus 1 minus, and again, I'm kind of plugging into this one, not this one. They're the same thing. This one is easier to plug into, though. So I have -1 over -1 quantity squared. All right, just have to evaluate this, and I'm done. First thing I see, -1 squared. Anything to an even power is always going to be positive. So this is a positive 1, which is just basically nothing, because when you multiply by 1, it's just not there. So I really have a -3. I can rewrite this down here. I have -3 plus 1. And then with this guy right here, I have the same term. -1 squared is just 1. 1 over 1 is 1. And then I'm going to subtract that 1. So -1. -1. And you can clearly see that the 1 and -1 do cancel each other out, leaving you with just -3. The correct answer here is D. Number 18, the graph of the function is shown above, which the following is true. All right, I'm going to underline that true because sometimes it's asking the opposite. So that means most of these things are going to be false. When I'm reading A, I'm noticing that both of these are going to be double-sided limits. This is as I approach A from both the left and the right. So as I approach A from the left, I seem to be approaching this height of 2, and when I approach it from the right, I seem to be approaching that same height of 2. The left and the right match each other, and that's a good thing. So in terms of that height was 2. So I can say that this one was 2. the limit of f of x as x approaches a from both sides is 2. What about for b? So for b from both sides, as I approach this coordinate b from the left, I seem to be approaching a height of 2. And when I approach it from the right, I seem to be approaching a height of 1, which don't match. These are different heights. Whenever they don't match, the answer is does not exist, D and E. And does 2 equal D and E? It does not, so it's not A. What about B? B, we just did that. We did it up here. We said, yes, that is equal to 2. So that one is actually the answer. That one is true. That means the rest of them have to be false. Let's go ahead and analyze why that is the case. So we already know that the double-sided limit of b, we just did up here, they were different values, so that was a does not exist. So this one should have been a d and e. I should cross this one out and say that one should be a d and e, but it's not, so it's false. Cross out C. D is saying that it's equal to 1. It's just trying to get, oh, it wasn't 2, is it 1? No, it's still D and E. Come on, you got this. This one is false again. And then finally it's saying that the double-sided limit as x approaches a from both sides does not exist. Well, it does exist. That is not true. It should have been 2. So that one is also false, and it's not E. Moving on to number 19. All right, we have a bunch of values that can be used, and it's saying, okay, h is this function, which is a function within inside of a function. So we have, I'm going to go ahead and label this one is going to be the inner, and this one's going to be the outer. And I'm going to take the derivative of h, which means I'm going to be taking the derivative of all of that, and then I'm going to plug in 1. All right, so this is just that definition of how do I take the derivative? Well, you do the derivative of the outer, then the derivative of the inner, and you multiply those together. So it's outer times inner, and I will write that as well. So this is going to be, oh, I wanted in pen though. This is going to be the outer, the derivative of the outer, multiplied the inner, the derivative of the inner. So the derivative of the outer is probably the trickiest bit of all, but remembering to do dinner is sometimes the trickiest bit for some students. The doubter is still f prime of g of x. You still have that g of x on the original inside, and then the dinner is the derivative of g, which is just g prime. So this is going to be times g prime of x. All right, and now we just plug in 1. Everywhere you see an x, change it to a 1. So this is going to be f prime of g of 1 times g prime of 1. And I'm realizing that I'm going to run out of room. I'm going to go ahead and move everything over here. I think that's good enough. Okay, so what is g of 1? I'm trying to figure out this value right here, and I can see g of 1 is 2. So I'm going to change this g of 1 into a 2. I can say, okay, this is now going to be f prime of 2 times. And now I need to find what is g prime of 1, and g prime of 1 is negative 3. So I'm going to come up over here and say that's going to be equal to, in pen, negative 3. And finally, I need to figure out what is f prime of 2, and f prime of 2 is negative 4. So I'm going to swap that out for a negative 4 times a negative 3. Negative times negative is a positive, and 4 times 3 is a positive 12. So the correct answer here is D. Number 20. I have this function, and I'm trying to take the derivative, and I'm not plugging anything in. So just take the derivative. Do we know how to do that? And the first thing that I'm noticing is that we're in eHouse, which makes me happy, because the doubter for eHouse is just eHouse. But then I always have to remember to do dinner, which is the tricky bit. So I'm going to go ahead and write out, well, this is just e to the 2 over x. But now I need to multiply that by the dinner, the derivative of the inner. And now I need to rewrite this inner. Instead of writing this as 2 over x, I'm going to write that as 2 times x to the power of negative 1. I don't like the fraction there because I need to take the derivative, and I don't want to use quotient rule because quotient rule is rough. Now I'm ready to go. I don't have to use quotient rule. I can just use your normal powerhouse. The powerhouse states that I'm going to multiply that number down in front, so I'm going to have a negative 2, and then I'm going to go down a power. So this is going to be times negative 2 x to the power of, and it goes down a power to negative 2. And I can rewrite that a little bit. So in the top, I have a negative 2. I'm kind of just rewriting this thing right now, and then I'll deal with this in a sec. So I have a negative 2 all over x squared, and then I need to multiply that by e to the 2 over x. And oh yeah, I think that's just D exactly as I wrote it. Cool. Moving on to number 21. Okay, so They write this a little bit strange, and this is a common thing in mathematics that I don't like. The way that you want to interpret this is y is equal to cosine of 3x, and then that quantity squared. That's really what's going on here. So I strongly recommend to do what I'm doing. If you see cosine squared or sine squared or tangent squared of something, to rewrite it like this, and then you can be like, okay, if I'm trying to take the derivative, and that is what's being asked for us, dy dx means take the derivative. That's the equivalent of saying, what is y prime? When I take the derivative, I first drew the outer house, which is the squared, and then I worry about the inner, and then there's an inner that I have to worry about. So a lot of things to do here. So the first thing, deal with the power house. The 2 comes down in front, and I'm now going to have 2 times cosine of 3x, and now I'm going to go down a power, goes down to the power of 1. Cool. So that is your outer. Now I can label that to outer. And then I'm going to multiply by the inner. The derivative of the inner, well, everything on the inside is the inner. The derivative of cosine is negative sine. How do I know it's negative? Well, because C here stands for change the sign. And if I have an antiderivative, it would be anti-change, which means same. But it's going forward, so it's just normal change, C for change. So it's going to be multiplied by negative sine of 3x. And notice that we haven't touched the 3x yet. That is the inner. So now I need to multiply this by the inner. This can be multiplied by the derivative of the inner. And the derivative of that inner, well, the inner is 3x. The derivative of 3x is 3. So that's going to be times 3. And the cool thing about multiple choice questions is there's always usually a shortcut. Once you have all that written out, you can be like, okay, well, let's just do the first part. I have a negative, I have a 3, and I have a 2. Those multiply together to get a -6. No -6, no -6, no -6, a +6. There's our -6. The correct answer is A. And you can see that the rest of that equation does match what we have up here. So we're good with that. And I should probably erase that line. Yeah, looks good. Whoa, turn that back off. Number 22. All right, the function is defined above. C and D are just some constants. Again, when you think of the word constant, that just means they're a number. And it's differentiable, and I'm trying to find the value of C plus D. All right, so when I see the word differentiable, that means 2 things to me. 1, it means it's differentiable, and 2, it means it is also continuous. Differentiable means it is also continuous. So it's 2 things, which means we can use both the continuity test and the differentiability test. They're both basically the same test. So I need to have the derivative for the differentiability test. So I'm going to take the derivative right now. I'm going to just write that right here. F prime of x. The way that you take the derivative of a piecewise function is you just take the derivative of each of the pieces. So I see this right here. I'm going to take the derivative of cx plus d. Again, the derivative is going to make constants go away, so I don't have a d. And the derivative of a linear term like 1x or 2x is just you take that coefficient. So for example, the derivative of 2x is 2, the derivative of 3x is 3, the derivative of cx is c. So the answer here is just c. And now I need to take the derivative of the right piece, take the derivative of this thing. So I have an x squared is going to turn into a 2x, and very similar to the last problem where I had the derivative of cx was c, the derivative of negative cx is negative c. So I'm going to say minus c. Cool. So I have our functions, and really I should kind of copy paste well, it's for that value, and I should put that right here, but I already know that, so I'm going to be lazy in my work. All right. I am ready for the continuity test. I am ready for the differentiability test. Which one looks easiest? I think the one with less x's looks easiest. I'm going to go ahead and do the differentiability test first. The differentiability test sounds hard, but it's really not too hard to do. You just set the left equal to the right, equal to the actual derivative. But in this case, the left and the actual slope are the same because there's this equal to sign down here. So really, I'm just setting the left equal to the right. I'm saying c is equal to 2x minus c. All right. And then after I do that, I'm going to plug in the suspect point. The suspect point is this value of 2 over here. So plug that in for x, and I get c is equal to 2 times 2 minus c. All right, I'm going to add a c to both sides, so I get a 2c on the left-hand side, no c's on the right-hand side, but I do have 2 times 2, which is 4, and therefore c is going to be equal to 2. which is half of the battle, because notice I need the value of c plus d, and I have c. Now I just need to find d, and guess where it's going to come from? The other test, the continuity test. The continuity test is basically saying the same thing as the differentiability test, namely I'm going to set the left piece equal to the right piece, and which is equal to the height because of that equal to sign. So set them equal to each other, plug in the suspect point. So I'm going to have a cx plus d, which I'm going to set equal to an x squared minus cx. And all of those x's are going to swap out for 2's. So I'm going to have 2c plus d is equal to 2 squared minus 2c. And hey, we know the value of c. We did it already. C was equal to 2 over here. So I can come back up here and say that c and that c are both a 2. So I can substitute yet again, and I get 4 plus d is equal to 4 minus 4. And 4 minus 4 cancel each other out on this right-hand side. So this is just a giant 0. Subtract 4 from both sides, and d is equal to negative 4. All right, so I know that d is equal to negative 4, c is equal to 2, d is equal to negative 4. Add those together, and I get negative 2, the correct answer. Number 23, we have an equation. We want to know what happens when x is equal to 2, and we're trying to take the derivative. We're trying to find y prime. Again, whenever you see dy dx, that's essentially asking, what is y prime? So let's go ahead and just immediately take the derivative. We could try to rearrange some things on this left-hand side. For example, we could like subtract an x squared from both sides, but it doesn't really matter. It's going to be the same net problem. So taking the derivative with respect to x, and that is kind of important because we are going to have like a y prime that'll pop out right here. So just be careful of that. The derivative of x squared is 2x. And then I need to add the derivative of x times y. Okay, so careful. We have two variables. They're being multiplied together. That's product rule. Product rule is 1d2 plus 2d1. And I can write that up above so that we can follow the work that I'm going to do. 1d2 plus 2d1. So what is 1? 1 is x. What is d2? Well, y is 2. So the derivative of y is y prime. Plus, and then 2 is y. d1, the derivative of x is 1. So y times 1. All right, I have all the derivative taken on the left-hand side, the right-hand side. The derivative of 10, well, it's just a constant, so it goes away, it goes to 0. All right, now I just need to solve for y prime. And I can immediately plug in x is equal to 2. So that's a problem, though, because I can see that's going to turn into 2. That's going to turn into 2. I'm solving for y prime, but this y right here, how do I get rid of that y? And here's the other thing that I should be doing. I should have plugged in that x equals 2 right away, because if this x is 2 and that x is 2, that leaves one variable, one unknown variable, which I can solve for, and then I'll get y, which means I can plug that y in over here. So let me go ahead and go do that right now. If I change this, so it's going to be 2 squared plus 2 times y is equal to 10. I can solve this. 2 squared is going to be 4. So this is 4. I'm going to subtract that 4 from both sides. 10 minus 4 is 6. So my new equation is now going to be 2y is equal to 6. Therefore, y is equal to 3. Now I'm ready to plug in a bunch of things over here. So y is 3, x is 2. Let's plug all those in. I get 2 times 2 plus 2 times y prime plus 3 is equal to 0. And I'm going to solve for that y prime. Again, my logic here is plug in as soon as you can. I don't want to do any sort of algebra manipulation because I might make a mistake, and it's easier to just play with numbers instead of variables, in my experience. Maybe you like variables, though. All right, so simplifying, I have a 4 here that's added to a 3. That's going to be a 7. And I can move that to the right-hand side, so I'm going to have a negative 7 on the right-hand side. So I'm going to have a 2y prime is equal to a negative 7. Finally, divide both sides by 2, and you get y prime is equal to negative 7 halves. And negative 7 halves is A. Final answer. Number 24. All right, it tells us our y value, and it's just asking what is y prime. Again, dy dx is the same thing as what is y prime. So you just take the derivative of this side, but you have to be careful because we have some multiplication happening. This is really x squared times sine of 2x. So I have a variable times another thing with a variable. This is yet another case of product rule. So I'm going to write this out. 1 d2 plus 2 d1. All right, so 1 is x squared. I can just rewrite that. And d2 is, there's a bit of work to do there. So the first thing, the most outside house here is the sine, and then that's my outer. My inner is going to be my 2x, so I need to do outer times inner. Or I should say doubter times dinner. There we go. So doubter, the derivative of sine is positive cosine. So this is going to be times positive cosine, still of 2x. And then I need to multiply by the dinner. The derivative of 2x is 2. And then I can move all of this stuff over here. Now I can say plus 2d1. So 2 is sine of 2x. Sine of 2x. And the d1, the derivative of x squared, is 2x. 2x. And there's our final answer. And you'll notice that doesn't look like any of these options down here. In fact, it's probably not A or B because those are too simple. It's probably one of these things, and notice that all of them have a 2x that's factored out, so let's also factor out a 2x. When we factor out a 2x, we're left with what on the inside? I'm left with one copy of the x and then all this cosine of 2x. So it's going to be x cosine of 2x plus, okay, if I factor out that 2x, that means this 2x is gone, just leaving us with the sine of 2x. So sine of 2x, and now we can see our answer. Where is it? It is going to be x cosine of x, and that's going to be a positive. So notice that this is x cosine of x with a positive. It's not the negative, so it is going to be E, final answer. Number 25. All right, we've got a graph with f and g. And so we're creating a new function, h, and you just multiply f and g together. And we're trying to find h prime of 3, which means take the derivative, then plug in 3. So take the derivative of this, then plug in 3. And again, we have two different functions, two things with an x on the inside that are being multiplied together, which means you're using product rule. And then after we do product rule, we're going to plug in 3. So what's really going on here? Well, this is going to be 1 d2 plus 2d1, that's product rule. 1 is f of x. d2 is g prime of x, plus 2, which is g of x, times d1, which is f prime of x. And then for each of those x's, we're going to plug in a 3. And I'm realizing this is nowhere near enough space, so I'm going to move all of you up here. So plugging in a 3 means the thing that we're finally after, we're trying to find what is f of 3 times g prime of 3 plus g of 3 times f prime of 3. And there's a lot of things that we need to do here, 4 to be exact, and it's all 4 of those values. So let's go ahead and do some analysis. I need to find both f of 3 and I need to find g of 3. Those are just heights, which we can do right now. So f of 3, what is the height of 3 on f? And then you can see over here at 3 on f, that has a height of 1. So I can say f of 3 is equal to 1. What about g of 3? G of 3 is the height at 3. So I can say, okay, on g at 3, it comes up to this spot, which has a height of 3. So I'm going to come over here and say that is equal to 3. And I'm realizing I don't need all that room, so I can move you guys over. Yeah, right there is good enough. Okay, what about f prime of 3? And what about g prime of 3? Remember, the derivative in terms of a graph is the slope. So really, it's doing kind of those same points. So at 3 on f, it comes up to this point. At this point, what is the slope of the line? What is the slope of this line right here? That was a terrible line. But what is that slope? And you'll notice that we have some nice lattice points. I have a lattice point here, here, and here. And I can choose any pair of them. I'm just going to choose these two arbitrarily and say, okay, we have this triangle. And that triangle is going to be, it goes down 1, right 3. Down 1, right 3 means down 1, right 3, negative 1/3. What about g prime of 3? So g prime of 3 means I'm still at 3. I'm going to come up to the g prime, and I need the slope of this line right here. The slope of that line goes right 1, up 1, or I should really say it goes up 1, right 1, because it always goes y over x. So up 1, right 1. And this is going to be up 1, right 1, which is 1 over 1. Cool, we're ready to plug in all these values. So coming back over here to the left-hand side, plugging in for f of 3 first. F of 3 we said was 1, g prime of 3 we said was 1, plus g of 3 we said was 3 times f prime of 3, which was negative 1/3. All right, 1 times 1 is 1, 3 times negative a third is negative 1. 1 plus negative 1 is 0. Kind of anticlimactic. I was expecting some cool things to happen, but we do get the final answer as C, 0. Number 26, the slope of the line tangent. All right, so the first thing that I used to think was, oh, we got a tangent line. Tangent line means y minus box is equal to m times x minus box, this equation. That's not right, because we're only asking for the slope, so we're only asking for this m value, which is just doing slope. You don't have to do any fancy equation. We're just saying, what is the derivative, and plug in 4. That's essentially what this graph is, or this question is asking for. So take the derivative of this, plug in 4, we're ready to go. So the derivative of log house is going to be 1 divided by whatever the inner is. Oop, I should have done eraser there. So it's going to be, and really a better way to think about that is really flip. Instead of 1 divided by x over 2, it's really flip of x over 2. So it's 2 over x. That is the derivative of log house, and then I still need to multiply by the derivative of the inner. So the inner is x over 2. The derivative of x over 2 is a half. So this is going to be multiplied by dinner, which is 1/2. So that's our function, which I can simplify because the 2 and 2 do cancel each other out, leaving me with just 1 over x. 1 over x. Okay, now I just need to plug in 4 for x. 4 turns into x. This is going to turn into 1 over 4. And that is our answer, B. Number 27. We have a bunch of y squareds and x y's all mixed together, and we're asked to find y prime, dy dx. So let's just take the derivative and see where that leads us. We're not plugging in any number like we did back in number 23, so it's a little bit more algebraic manipulation, but we'll be careful about that. So y squared, we get 2y, and then y prime. Don't forget about your dinner. Your doubter was that powerhouse here, this y squared, so that turned into the 2y, but then you need to multiply by the inner of that house, which was just y. The dinner of y is y prime. Okay, minus. Okay, so there's two kind of approaches to tackling the derivative of 2xy. The one that I prefer the most is to kind of think of that negative 2 factored out and just worrying about that x times y as a product rule by itself. So I'm gonna leave that negative 2 factored out by writing negative 2 right here, and then I'm gonna put parentheses, and now I'm gonna worry about what is the derivative of x times y, which I do have memorized. But if you don't, this is how you think about it. It is still product rule. It's 1 d2 plus 2 d1. So 1 is x, d2 is y prime, plus 2, which is y, and d1, which is the derivative of x, which is just 1. All right, that's the left-hand side. Right-hand side, we need to take the derivative. The derivative of 16 is 0. All right, so I need, remember what you're trying to solve for. We need to solve for y prime. So I need to somehow grab these y primes, keep them on one side, and move everything else to this side. That's our general strategy. And it does mean I'm going to have to distribute this negative 2. I thought I could get away without doing that, but I'm going to do that right now. So I have 2y y prime minus 2x y prime, and I'm still distributing that negative 2 into this last term. So I'm going to get a negative 2y equal to 0. All right, anything that does not have a y prime term in it, looking at you, negative 2y, you need to move to the right-hand side, and then we're going to do some cool math over here on the left. So I'm running out of room. I think I can do it all the way over here. So I'm going to now say I have 2y y prime minus 2x y prime is equal to a positive now 2y, because I moved it to the right-hand side. I added 2y to both sides. Now I need to get the y prime term isolated, and to do that I'm going to factor it out. So I'm going to say y prime is being factored out, and what's left over is a 2y minus 2x. The right-hand side hasn't changed, it's still 2y. And now I can divide both sides by this 2y minus 2x to get that y prime by itself. So when I do that, I'm left with y prime is equal to 2y, all of that divided by 2y minus 2x. And you'll notice that both the top and bottom have a 2 that we can factor out. In fact, I should have probably done that all the way back where maybe right here. I can divide everything by 2, divide by 2, divide by 2, divide by 2 to get rid of all of those 2's, or I could just do it right here, get rid of all those 2's, and I can simplify this as y all over y minus x. So y all over y minus x, is that an answer? It is an answer. So I'm going to go ahead and say our answer here is C. And you might have a different answer than me. And I want to talk about why. You might have this answer where instead of having y over y minus x, you might have solved it a different way and gotten this answer. You might have gotten negative y all over, maybe you said x minus y. This is correct. And watch how I can convert your answer right here into my answer over here. I'm going to multiply your answer by multiplying by, why am I doing this in laser pointer? Multiplying the top and bottom by -1. And notice what I get. I get a positive y on the top, and I get a negative x plus a y, which is exactly what I have over here, just in a different order. I put the negative x second instead of first. So it is the same thing. Just be wary that that is a correct answer, but it's just not listed in the multiple choice. If that ever happens to you, multiply the top and bottom by -1, which is still multiplying by 1. You're allowed to do that, and you should get the right answer that they're looking for the multiple choice. Number 28. The instantaneous rate of change, the function at 3 is, all right, so the first thing that I notice is that we have this keyword, instantaneous rate of change. Make it into a line, thank you. And that is synonymous with derivative, or slope, as the slope of the tangent, right? So it's essentially asking us, take the derivative of this thing, plug in 3. And this thing is a fraction. We have no way of turning that into a non-fraction aside from maybe turning that into product rule, which is about as gross as product or quotient rule anyway. So I'm just going to use quotient rule. As a reminder for quotient rule, it is low times d high, or low d high, minus high d low, all over low low, or low squared. All right, so for s, the low is x plus 1. The derivative of, did I say die? D high. Sorry about that. And the derivative of d high, the derivative of the top is going to be 2x plus 2. Subtract the derivative of the low, which is going to be 1, times, why did I say d? Okay, I did that a little bit backwards. I apologize. I should have high d low. So high is x squared plus 2x. And then I do d low. D low is just times 1. And then all of that's going to be divided by low low, which is x plus 1 quantity squared. All right, so we've taken the derivative. As soon as we can plug in that x is equal to 3, do it as soon as you can. And I can do it right now. All of these x's are going to turn into little cute 3's. All right. This is going to be equal to 3 plus 1, which is going to be 4, times 2x plus 2 is going to turn into, it's going to be 2 times 3, which is 6. 6 plus 2 is 8, so 4 times 8, minus, and then do some more mental math. 3 squared is 9. 9 plus 6 is 15, so 15 times 1 is 15. That's all going to be divided by, then 3 plus 1 is going to be 4. 4 squared is 16, so I have 16. 4 times 8 is 32, and I can do some more mental math. I don't have to do that in different steps. Oops, I meant eraser. 4 times 8 is 32, minus 15 is 17, so I have 17 over 16. And that should be an answer, I'm hoping. Ah, there it is, B, final answer. Number 29. All right. Decreasing. Okay, so decreasing, we need a speechy definition for decreasing. Decreasing is wherever you take the derivative of the thing you're talking about. If we're talking about f, then the derivative of f is f prime. So where f prime is negative, is less than 0. So I need f prime, and I don't have f prime. And notice that when I'm trying to take the derivative, I have two different x's that are being multiplied together. So it's going to be product rule. That's going to write 1d2 plus 2d1. And fill this in. All right, so 1 is x squared. D2 is, I love eHouse, it's just e to the x again. Plus 2, which is e to the x again. And D1 is times 2x. Okay, we need to figure out where, we've taken the derivative, where is this derivative less than 0? And I think I'm going to clean this up a little bit. There's two steps I can do. I'm going to first factor out this e to the power of x. So when I factor that out, I'm left with e to the power of x, and what's left over is x squared plus 2x. And actually, I'm going to leave it like that. And I need to find where that thing is less than 0. So let's find where it's equal to 0 first, and then I'll make some bounds on this thing. So set this equal to 0. Just remember that e to the power of x can never be 0. It's always positive. And if it was a negative e to the x, it would always be negative. Mainly, it can't be equal to 0, so I'm just going to kind of ignore it for now and set this thing equal to 0. So from there, I'm going to have... I'm going to factor this at the same time, so it's going to be x times the quantity of x plus 2 is set equal to 0. Again, I just set this equal to 0, but I factor this at the same time. And when I do that, I get x is equal to 0 or x is equal to negative 2. Both are valid solutions. And then I make a number line. So my number line, straight line, go. Yep. And then I have negative 2 right here. I have 0 right here. And then I do some sort of test point. I don't know, a good test point I think is like 1. If I plug in 1 into the original function, and I'm thinking of the original function kind of like right here. If I plug in 1, this is always going to be positive, so I don't have to worry about that. 1 squared is 1, plus 2 times 1, which is plus another positive. It's going to be positive. I know that up here I have a positive value. And because each of these factors up here are to the power of 1. That's the power of 1. That's the power of 1. That means it's going to be odd powers, right? Odd powers mean that when you move over that critical value, it will switch signs. If this was an even power like 2 or 4, it would not switch signs. But we know it does. So it's going to switch to a negative and switch to a positive. So now we know where we have increasing and decreasing intervals. Decreasing intervals are wherever we have negative, and increasing, which we don't care about, are those intervals. So our answer is between negative 2 and 0. Where do we have? Okay, negative 2 and 0 is B. All right, number 30. What are all the values where we're increasing? Okay, so increasing deserves a speechy definition. That's where we take the derivative of the thing we're talking about. The thing we're talking about is f. So f prime is the derivative, f prime, and that needs to be greater than 0. It needs to be positive values. So first we need to find the derivative, set it equal to 0, and then kind of do the same thing that we did in the last question, but the answer now is going to be all the positive ones instead of all the negative ones, right? So first, take the derivative. If I do the derivative, this is going to be f prime of x is equal to, okay, 3 comes down in front. It goes down a power to 2 plus 2 times 3. Again, this 2 comes down to the 3, 6 times x, and it goes down a power to just 1, which I'm just going to leave as nothing, minus 9, and that's all we have. So I can rewrite that a little bit nicer. This is equal to, I can factor out a 3. 3 times the quantity of x squared plus 2x minus 3. And I can write that again because I know that I can factor that with a ninja star in my head. That's going to be x plus 3, x minus 1. Yeah, x plus 3, x minus 1. And if you can't do those in your head, I will go ahead and write out my work. I'm doing a ninja star. What times what multiplies to negative 3 and adds to 2? Well, your answer for that is 3 and negative 1. 3 times negative 1 multiplies to negative 3, and 3 plus negative 1 adds to a positive 2. So that's where these values came from right here. All right, I have this nice and factored. Now I can set that equal to 0. So if I set that equal to 0, ooh, I want to go back to my blue though. So I'll say 3 times x plus 3 times x minus 1. We're going to set that equal to 0 and solve. So if I divide both sides by 3, it's as if that 3 never existed. And then our answers are going to be x is equal to negative 3 and x is equal to 1. So set up our number line, find our intervals. Number line, boom. We have negative 3, we have 1. And what are some good test values? Well, I particularly really like 0 as a test value. When we plug in 0, again, you want to be plugging in 0 to some sort of original equation. A lot of people make the mistake of, oh, I'll plug it in when I don't have that 3 or something. I'm going to plug it in right here. The thing that will get you in trouble is if there's a negative 3 that you kind of ignored, because then that one will always be negative and all of your values will be switched, but we don't have anything to worry about in this case. So when I plug in 0, I have a positive. 0 plus 3 is a positive, and 0 minus 1 is negative 1, which is a negative. Multiplying all 3 of these together, I get a negative value. Ooh, I don't mean to do that. So it's a negative value right here. And again, because we have an odd power and an odd power for each of those critical values, every time that we move over that critical value, we are going to switch signs from a negative to a positive, which means we have a positive right here and a positive right here. All right, we're looking for where we are increasing, so we are looking for the positive values. So our answers are going to be everything to the left of -3 and everything to the right of +1. So less than -3 and greater than 1. And you can see less than -3, greater than 1, that is the answer that we're looking for. Answer C. I did want to do that in blue though, so I can come back here and say C. All right, 31. How many critical points does that function have? So it's important to know the Speechy definition of a critical point. So an F critical value, or critical, I guess it's not a point, it's a value, but it's the same thing. An FCV is, there's two parts, right? It's wherever the derivative of the thing we're talking about. If we're talking about F, then it's F prime. It's where F prime is equal to 0 or where F prime does not exist. And notice that the only thing that can make us not exist is if we had a fraction with like divided by x or something where that x could be 0. But because we don't have any fractions, we don't have any second part of the definition. We're just strictly looking, if I set that equal to 0, how many do I have? And if I set that equal to 0, I get x is equal to -2, x is equal to 3, and that's it. So there's two of them. Remember the distinction between these problems by the way, which is if this was asking for relative extremums, then it would change the definition to where do you have a sign change, and you can only have a sign change where you have an odd value. So this would have been a sign change, and this would not have had a sign change because we have an even value. In that case, we would have only had one relative extremum. But because this is an easier question, it's just critical value, just count how many of these factors you have. 1, 2, answer's 2. All right, number 32. By the way, when we're done with number 32, we are halfway done with the packet. I think there are 64 questions in this packet. Number 32 is one of the most tricky questions in the entire packet. And I gave very little room for it, so I apologize. The reason though it's so tricky is because it's asking for the absolute max. So if I was asking for the relative max, then we could just use the definition of relative max. Absolute maximum means we have to make a table. So there are two ways of going about this. There's the slow and dumb way, which I will do first, and then there's the fast way, which I will show second. So I'm sorry, number 33, but I am divvying up your area, and I'm going to say everything over here is technically part of number 32 because I need some room. So over here, I need to do this the slow way, which is setting up a table. My table is going to have values of x. I'm going to have start plus change is equal to end, which is a little bit misleading. But there's going to be my table. Boink, boink. Got our table looking pretty good. We always need our start and our end. We always need -2, and we always need 4. And then we need all of the relative extremums. And to find relative extremums, you need to take the derivative and start setting this equal to 0. So let's do that. I think I have room up here. So f prime of x, I need to take the derivative. That's going to be 3x squared minus 6x, and then the 12 just kind of disappears. So if I were to factor out a 3, I'm left with 3 times the quantity of x squared minus 2x, and I'm realizing I really should have factored out a 3x instead of a 3. So let me do another step again. It's going to be 3x times x minus 2. There we go. I'm going to set this thing equal to 0, which will find critical values, but I'm really after relative extremums. But the intermediate step to find relative extremums is to first find the critical values by setting this equal to 0. So if I say 3x times the quantity of x minus 2, if I set that equal to 0, I get x is equal to 0, and x is equal to 2. Those are my two critical values. And notice that both of them are going to be relative extremums, and the reason for that is because this is to the power of 1, this is to the power of 1. Ones are odd numbers, and odd numbers means we are going to have a sign change, and therefore it is a relative extremum. So we need to include 0 and 2 on the table. And here is where I want to pause and talk about the shortcut. The shortcut would have been just do that from the very beginning. You don't have to do all this work. The only possible values for our table are these possible values right here. Notice you do have to do a little bit of extra work because there's a random 1 on there, which would have been added to your table, but it would have been so much faster to just jump to this step, do no calculus, and say, okay, those are the values I'm comparing. That's how I would have done this problem, but I want to show you the slow way. That is the full mathematical analysis that we're going to be doing. And then you might be asking, start plus change? What is he talking about? There's no start condition, and you're right, the start is going to be 0 for all of these. And there's not really a change. Really all I'm doing is I'm plugging in -2 to figure out which one is bigger. So essentially I'm just going to take our old equation here and plug in value of -2, then 0, then 2, then 4. And that's a little bit of work, but it's not too bad. So it's going to be -2 to the power of 3 minus 3 times -2 to the power of 2 plus 12. Same thing down here. I'm going to get 0 cubed minus 3 times 0 squared plus 12. Then I'm going to get 2 cubed. Oh, I don't know why I'm writing a minus. I can just hit the undo button. That's much faster. Minus 3 times 2 squared plus 12. And finally, 4 cubed minus 3 times 4 squared plus 12. Whichever one is the biggest wins. All right, so first up, I get -8, and I have this -2 squared, which is 4. 4 times 3 is 12, so I'm going to be subtracting another 12. Subtracting a 12, adding a 12, which is -8. Not a great choice, because I know we can get a positive number at least. That's going to be 12, because 0 plus 0 plus 12. This is going to be 8. Minus, it's basically the same thing, 8 minus 12. Again, the math came from doing 2 squared, which is 4. 4 times 3 is 12, minus that 12, right? And then plus 12 again. So plus 12, ooh, that was a 2, and this is a 12. 12 and 12 cancel each other out, leaving us with a positive 8, but still 12 looks like it's our winner. So you might be thinking, it's 0. And that does make sense with our analysis if we did like where does it change from a positive to a negative? But check this out. This is the answer down here. It's going to be 4, because I'm going to get 4 cubed, which is gigantic. That's going to be 16 times 4. That's 64. 64 minus, okay, 4 squared is 16. 16 times 3 is 48. And then plus 12. So I think first I'm going to do 64 plus 12, which is 76, and then 76 minus 48. Oh, math is failing me. It's going to be equal to 76 minus 48, and that's going to be 28. And 28 is bigger than all the rest, so the answer is 4. 4 is the absolute max. This is just one of those times to remember that you do have to include the start and the end, the -2 and 4, when you're comparing absolute maximums. All right. Whew, halfway done with the packet. Let's go. All right, number 33. We're looking for concave down. So it's helpful to know the speech sheet definition of concave down. F concave down is wherever you have the second derivative of the thing we're talking about, in this case f double prime, and that has to be less than 0 or negative. I know people don't really like that definition. They kind of like saying f double prime negative, kind of like that. Whatever floats your boat or sinks your sub. So I'm going to have to find the second derivative, which is kind of annoying because I have a fraction here. Or do I? You can go ahead and rewrite this thing and say that this is y is equal to 2 times the quantity of 4 minus x to the power of -1, and you don't even need to do product rule, because you can just take the derivative of this over and over, and then you multiply by 2 at the very end. So if I do that, y prime here, the first derivative, there's a 2 again, and then I'm going to do our powerhouse rules. Powerhouse states that this -1 is going to come down in front and then go down to power. So I'm going to be -4 minus x, now to the -2, and then I need to multiply by dinner. The derivative of the inner is a -1. All right, I need to simplify this before I take the derivative again, otherwise it's going to get too messy. So this is going to be, first I'm noticing that I have a negative times a negative, which are going to cancel each other out, so that's gone. And really I'm just left with a 2 in the top times, and I'm not going to make this as a fraction. I realize that I still don't want a fraction because I'm going to take the derivative again. It's going to be 2 times 4 minus x to the power of -2. All right, now I'm ready to take the derivative again. Y double prime is equal to, all right, so again, that 2 is still kind of stuck out front, and I'm going to multiply that. Again, this will still be multiplied. Multiplied by a -2 comes down in front, times 4 minus x, now to the power of -3, and then multiply by the derivative of the inner, which is dinner, -1. There is the second derivative. Again, just like the last problem, negative and negative cancel each other out, so there's no negatives here. And if I rewrite this with a fraction, which will be helpful now, I have 2 times 2, which is 4 in the numerator, and in the denominator, I have 4 minus x, all of that to the power of 3. So there's a second derivative, and I'm going to look for critical values. So for critical values, the definition for critical values, I think I wrote up here somewhere, is these two, right? Where f prime is equal to 0 or doesn't exist. The problem with this one is it can never be 0 because the top is 4. It's essentially, these two definitions come from set the top equal to 0, set the bottom equal to 0. So set the top equal to 0, can't happen. Set the bottom equal to 0. That does actually help us. So I'm going to say for f double prime dne happens whenever 4 minus x to the power of 3 is equal to 0. And if I solve that, I cube root both sides to get 4 minus x is equal to 0. Add x to both sides to get 4 is equal to x. All right, so we've done a lot of math now, and I realized that we could have conserved space if I went like this. If I grab all that and move it up a little bit, it kind of is like a nice puzzle piece there. And then I can do my final analysis by doing a number line down here, make it straight, and do, oh, there's only one value, so I might as well just make it right in the center. There's one value that we need to test at 4. So with the original function right here, when I plug in a number that is bigger, like, I don't know, or let's do smaller, that's much easier. If I plug in a number like 1, do I get a negative or a positive? And we know that because we have an odd power here, it's going to flip signs from a negative to a positive or vice versa, from a positive to a negative. Plug it in 1, what do we get? So plug in 1 goes right here. So 4 minus 1 is 3, and 3 is positive, positive to the power of 3 is still positive, positive divided by positive is positive, all of that stuff should be a positive. Then I'll switch signs to a negative over here. And that makes sense because if you choose a number like 5, then you'll get like 4 minus 5, which is a negative. Negative to the power of 3 is a negative. Positive divided by negative is a negative. So after all that analysis, what have we discovered? It's concave down whenever we are over here, whenever we're bigger than 4. So where does it say bigger than 4? Bigger than 4 is E. And I want to do that in blue, E. All right. And then we're moving on to number 34. The function is having a relative maximum. Okay, relative maximum is much, much easier than absolute maximum because we don't need to make a table. We just have to use the definition of a relative maximum. The definition of an x relative, or for an f, yeah, f relative max. Where do I have room? F relative max. I'll do right here. F relative max is you take the derivative of the thing we're talking about. We're talking about f, so the derivative of f is f prime sign change from a positive to a negative. So to do that, we need to get f prime, set it equal to 0, and find where those boundary points are between positive and negative values. So there's f of x. Let's take the derivative, f prime of x. That's going to be a 3x squared minus 6x. And I'm going to go ahead and factor that. I can factor out a 3x, so it's going to be 3x times the quantity of x minus 2. And I'm going to set that equal to 0, and that will find the boundary points between where you have positive and negative values. So if I set 3x times x minus 2 set equal to 0, that is going to give us x is equal to 0 or x is equal to 2. Those are our two little boundary points. Let's go ahead and make a number line to figure out what's going on with those points. So we have 0 and we have 2. Let's do a test value. A good test value I like is like 1. If I plug in 1 to this original function right here, I guess, yeah, I think that's fine. I really should be referring to this. If I plug in 1, I'm going to get positive times a negative, because 1 minus 2 is a negative. So positive times a negative is a negative. So it's going to be a negative right here. And notice that both of these powers here are 1 and 1, which means they're odd powers, which means I'm going to switch signs when I jump over those critical values. And this is going to turn into a positive and a positive. So again, we're looking for that original definition where we change from a positive to a negative, reading from left to right. So from positive to negative, boom, there's our answer right there at 0. Correct answer is B. Oh, I want to do it in blue. Number 35. We're looking for the x-coordinate of the inflection point. So inflection point, that is a speechy definition that we definitely need to know. So we're talking about f, inflection point. The definition of f inflection point is where you have f double prime sign change. So if we have y, we need to find y prime and y double prime. Y prime is going to be 3 comes down in front, 3x go down in power to 2, plus 2 comes down in front, 2 times 3 is 6, x goes down in power to 1, and that constant term of -1 just goes away. You're gone. Moving on to y double prime now, taking the derivative, the 2 comes down in front to multiply to the 3 to get a 6, x to the power of just 1, and then plus 6. Cool. So there is our second derivative. Let's set it equal to 0 to find where we have that boundary point for where we can have a sign change. So I'm going to rewrite this as 6 times the quantity of x plus 1 to help it be factored. And I'm going to set that equal to 0. So 0 is equal to 6 times the quantity of x plus 1. That only happens when x is equal to -1. And I'm guessing that's a sign change, and it is, because check this out. This power right here is the power of 1. 1 is an odd number. Odd numbers means you have a sign change. So you do have a sign change at -1. Therefore, it is the inflection point at -1. Number 36. All right, we have the second derivative already, and we're looking for the same thing, f inflection point. And we already have the definition for inflection points for inflection. We need an f double prime sign change, and we're going to use kind of that same analysis where we use the powers. This is a power of 2, power of 1, power of 1. Whenever you have an even power, you are not going to have a sign change. So this is not going to give us an inflection point, but these two will give us inflection points because they are two odd powers. So we'll have an inflection point only at 3 and only at 6. The correct answer here is D. Number 17. Some graphical analysis. So the graph of h of x is above. We're looking for which of the following could be h prime of x. So I think the easiest way to analyze this is to talk about the type of function that it is. So you look at the right end condition. On the right-hand side down here, this is going down, so it's going to be negative. So this whole entire function is a negative function, and then you can talk about the type of function that it is. Because we have these 2 points at which we turn around, it's going to be a cubic. If we had 1 point that we turn around, that would be a quadratic. If we have no points that we turn around, that would be linear. This is a cubic. So my full answer for the analysis of this graph is this is a negative cubic. And that means if I'm trying to find the derivative, again, I have a graph of h and I want h prime, I'm taking the derivative. Whenever you take the derivative, you get rid of one of these turnaround spots. So instead of having 2 of these bumps, you're going to have 1 bump. And that's going to give you one of those 3 options. It can't be D or C because those don't have the 1 bumps that we're looking for. So automatically eliminate C and D. All right, and we know that when we take the derivative or the integral of a negative function, you are still left with a negative function, which can now eliminate a because this is a positive function, so it cannot be a. B and E, if you look at their right point, it is a negative and a negative, so those are both negative. They're still in the running. How do we decide between these two? And for that, we want to look at the derivative of h. So h prime on a graph of h is slope. And are there any unique slopes on this graph that kind of stand out to you? The 2 that stand out to me are this slope and this slope at these points right here. I have a slope of 0 and a slope of 0, which means I should have a height of 0 and a height of 0. Over here, the only height of 0 that I have on E is in the center, but you don't have a slope of 0 in the center anywhere. So the final analysis is telling us that the answer is B here. Let's just move on to number 38. We have this graph. We're looking for where it's both increasing and concave down. So it's both of these, increasing and concave down. So we need both those definitions, and we're talking about G. So G increasing is wherever you have G prime is positive, or you can say G prime is greater than 0. Both of those definitions are the same. They're both equally great. And then where do you have G concave down? That's where you have a G double prime less than 0, or G double prime is negative. G double prime less than 0. Both of those, again, are equally the same definition. So we have a graph of G prime, and that's kind of important to note. This is G prime. It tells you the derivative of the function G is shown. So it tells you it twice, just in case you forget that this is G prime. So on a graph of G prime, what is G prime? That's going to be height. So I'll label those height. And then on a graph of g prime, what is g double prime? G double prime must therefore be slope. So essentially, we boiled down the question to ask, where do we have a positive height and a negative slope? Well, positive height means we're not anywhere down here. We have to be somewhere up here for positive height. So we're limited to up here, and then we have to have a slope that is negative. This is a positive slope up here, positive, positive, and then all of a sudden I have negative slope, negative slope, negative slope. So it's only talking about this piece of the graph up here between 0 to 2. So between 0 and 2, correct answer is going to be E. Number 39. Which of the following curves could be a part of the graph of f? Okay, so let's do the analysis. All of those are graphs of f. So f prime is going to be slope on a graph of f, and f double prime on a graph of f is going to be concavity. So it needs to have a negative slope, and we need to have a positive concavity. So let's do the slopes first. Which of the slopes are always negative? They have to be negative everywhere, because remember, whenever you have f of x, or f prime of x, that's saying f prime of x for all x. So we have positive slope, positive slope, positive slope, positive slope, but we want negative slope, so it's not A. B has, again, kind of the same problem where it's positive, positive, positive slopes, and we want negative slopes. Darn it, so it's not B. All right, C seems like it's doing a good job. We have always negative slopes. So far, so good. D has all positive slopes. Come on, guys. Your slopes aren't even right. And then E has negative slopes as well, just like C. So it's between E and C. Those are all negative slopes. So now we need the second part of the definition. The concavity always has to be positive. The way that you do concavity is you have to ask yourself, are you a smiley face or are you a rainbow? Notice that up here for C, you have concave up, but then it switches to concave down. You switch between the two concavities, and it has to be concave up everywhere. So it's not C, and notice that E is concave up everywhere, which means that is our answer. Answer E. Number 40. Okay, this one is a tricky question because I don't really teach this math, but I will review it right now. We need to have a positive first derivative, so I'll underline that. That's a key bit that we need, and we need a negative second derivative. Which of the following could be table values? So whenever you have table values and you're talking about positive and negative derivatives, it's really asking for positive and negative first and second differences. So let me go ahead and reinterpret this. A positive first derivative is the same thing as a positive first difference. And a negative second derivative means we have a negative second difference. So let's go ahead and look at these tables. So if I look at the first difference, so I'm just going to label this as 1 for first difference. 9 minus 7 is 2. And I don't know why I'm drawing my arrow, my I don't know what you call this, like a sideways carrot. To get from 7 to 9, you have to add 2, or you can say 9 minus 7 is 2. 12 minus 9 is 3. 16 minus 12 is 4. So is that a good thing or is that a bad thing? Those are the first differences, and all the first differences have to be positive, so that was good. This is in the running. Now let's go ahead and do the first differences for all the tables, and then we'll come back and do the second differences for the remainders. To get from 7 to 11, you had to add 4. To get from 11 to 14, you had to add 3. To get from 14 to 16, you had to add 2. So far, so good. Those are all positive values. But when I get C, 12 minus 16 is negative 4, 9 minus 12 is negative 3, 7 minus 9 is negative 2. Those are negative values, which means C is out of the running. All of these first differences, I should be labeling these as first differences. All the first differences have to be positive. That's what we're looking for, and those are not positive. So not C. What about D? Same thing. You're going to get a negative 2, a negative 3, and a negative 4, which means that you are out of the running. These are all negative values for the first differences, and we want positive values. And yet again, same thing. You get minus 3, minus 3, minus 3. All of those are negative first differences, which means it is also out of the running. Not D, not E. So we only have to do the analysis on A and B for the second differences. So that was the first. Now we're on to the second. So I'll label this 2, second, and second differences. The second differences, how do you get from 2 to 3? Well, I have to add 1, so that's going to be positive 1. Or you can think of this again, 3 minus 2. What is 4 minus 3? 1. That is a problem because we want the second differences to be negative. That's what it said up here. Negative second differences, and those are all positive, so it's not A, and by process of elimination, it is B. But let's see why. When we actually calculate these second derivatives, 3 minus 4 is negative 1, and 2 minus 3 is a negative 1. All the second derivatives are negative. And just check it out again. It's kind of cool. The first derivatives and the first difference is positive. The second derivative and second differences are all negative. The correct answer is indeed choice B. Number 41. We have the graphs of the derivatives that are shown above. We're trying to find which ones have a relative max. All right, so the main thing that we need to know is, I know that we're talking about f, g, and h, but I'm just going to do the analysis for f. When I'm doing an f relative max, that means I'm talking about an f prime, let's do a colon here, f prime goes from a positive to a negative. And it's easy to swap out, like g relative max is g prime positive to a negative, etc. And since these are all graphs of f prime, g prime, and h prime, we're talking about height. So height, because f prime in a graph of f prime is height. So for each of these, do you have a height that goes from a positive to a negative? And then you can see over here, we have, it goes from a negative to a negative. This one goes from a negative to a positive. And finally, we get a positive to a negative down here. So we have a max right here, and I'll go ahead and circle it. We have a max right there, good. For the next question, it never crosses only once and never crosses again, and it crosses from a negative to a positive, which is a minimum. So it's not going to be the second graph. And then for the last graph, it never even touches the x-axis. So how's that possible to even have it doesn't even have a critical value, let alone a relative extremum, let alone a relative max. So the correct answer here, it's only f, it's just A. Number 42. We have an equation for the line tangent, and how do you do that? Okay, so it needs to be tangent to that graph. So let's go ahead and first write out the definition of equation of the line tangent. That's always going to be y minus box is equal to the slope, which is going to be box times x minus box. Okay, in each of these spots we have an x-coordinate, we have a y-coordinate, which I'll call that f of x, and we'll have the f prime of x, which is the slope. All right, we know the x value. It tells us over here that the x value, that's the y value. The x value is 0, and the y value is 1, so I can fill in those values immediately. The y value is 1, the x value is 0, and now we just need to figure out the derivative when we plug in 0. So we have y, let's go ahead and take the derivative. Y prime is going to be 1, and then C stands for change, so change to a negative sine of x. Do we have to do dinner? No, dinner is 1, so you don't have to worry about it. And I need to plug in 0. So y prime, when I plug in x is equal to 0, is equal to, got a little bit of a mark there, 1 minus sine of 0. And sine of 0 is 0, so that's just equal to 1. So I can come back over here and say f prime of 0 is 1. And then I can simplify this a little bit. So this is going to be y minus 1 is equal to x. And I can add 1 to both sides, get y is equal to x plus 1. And the correct answer here is B. Moving on to number 43. All right, the equation of a tangent line to that graph at 1, 7 is, okay, so kind of same setup again. We're still dealing with equation of the line tangent, so we're still dealing with y minus box is equal to box times x minus box. And just like in the last problem, we have an x and a y coordinate. We have the x is 1, the y is 7, so 1 and 7. The tricky bit is finding the derivative and then plugging in 1 to get this middle box right here. So that is going to be, what is, I guess it's not really f prime because it's y, but whatever, I'm going to call it f. F prime of 1, essentially. Take the derivative and plug in 1. And the hard part about that is taking the derivative is going to require quotient rule. Let's go ahead and relist what is quotient rule. Quotient rule is low d high minus high d low all over low squared, right? All right, so low is going to be 4x minus 3. The derivative of the top, d high, is going to be 3 minus high, which is 3x plus 4, times d low, which is going to be 4. And then that's all going to be divided by low, which is 4x minus 3 quantity squared. And we can immediately plug in 1 for x. So every time you see an x, change that out for a 1. And that's going to be 4 times 1 minus 3, which is going to be 1 times 3 minus, okay, 3 times 1 is 3, 3 plus 4 is 7, so it's going to be 7 times 4. All of that's going to be divided by 4 times 1 is 4. 4 minus 3 is 1. 1 squared is 1, so 1. And that's really easy to simplify. We have 3 minus 28, which is a negative 25, really? Oh yeah, I see those in the multiple choice answer. Negative 25. Notice that they kind of have their y's and x's on the same side, so I can go ahead and simplify my answer down here and say that this is going to be y minus 7 is equal to negative 25x plus 25. I'm going to add the 7 to the right-hand side to get that into a 32, and it's going to be y plus 25x is equal to 32. And that is option A. Moving on to number 44. All right, which of the following is an equation for the tangent line to the graph of that? So again, same exact formula. Whenever you see equation of tangent line, you're thinking of y minus box is equal to box times x minus box. And they gave us the x and y value again. X and y are both the same. X and y are both 1, so I can fill in those values immediately. We have 1 and 1, and yet again we're going to do f prime of 1 goes in this box right here, which isn't as difficult. Again, it really isn't f, it's really y, but whatever. Y prime, and then I'm going to take the derivative, then plug in 1. It's going to be 4x to the power of 3 minus 3x squared minus 2x plus 1, and then that last one over here just goes away. It's a derivative of a constant. Now that we have our formula, we're going to go ahead and plug in x is equal to 1. So this is going to be, this is y prime when I do x is equal to 1 is equal to 4 minus 3 minus 2 plus 1. Minus 3 minus 2 is negative 5. 4 plus 1 is 5. So this is all equal to 0. And that means 0 is here, which is going to cancel out everything over here. That whole thing is going to be 0. So essentially I just have y minus 1 is equal to 0, or y is equal to 1. And that means the correct answer is A again. Moving on to the next question, number 45. For this function, it already took the derivative for us, and it tells us our x value is 1 and our y value is 4, and we're trying to approximate 1.2 using the tangent line graph. So the graph of the tangent line, or the equation of the tangent line, again, is going to be y minus box. Why did I write that? It's supposed to be equal to box, the slope, times x minus box. And we know the x value is 1, the y value is 4. And we have, they already took the derivative for us, which is nice. So I just need to plug in x is equal to 1 in for this x right here. So 2 times 1 is 2, 2 plus 1 is 3, which means that the derivative is 3. So we have our equation for the tangent line, and now we want to approximate 1.2. So I'm going to take this 1.2, plug it in for x, and see what that approximation is. So this is going to be y minus 4 is equal to 3 times, and this is the thing that I'm plugging in, 1.2, and then minus 1. And then this is just some mental math now. So 1.2 minus 1 is 0.2. 0.2 times 3, and I will write this down, is going to be 0.6 is equal to y minus 4. Add 4 to both sides. Y is equal to 4.6. Number 46. All right, we're talking about a sphere, and let's go ahead and annotate everything that we see in here. So the radius is increasing. Whenever we see these words, I want to zoom in so I can make my line a little bit neater. The radius is increasing means that it's talking about r prime, and it's increasing means it's positive. Decreasing would be negative. So that means that we have r prime is equal to 0.3 at the instant when the surface area becomes 100 pi. So that's just s is equal to 100 pi. Capital S is equal to 100 pi. What is the rate of increase in cubic inches per second of the volume? So if it's a rate of the volume, then that's talking about V prime, capital V prime. That's what we're after. I'm going to leave that as our empty box, or you can say like question mark. That's the thing we want to try to solve. And it gives us some formulas, and I have a feeling we're going to use both of those. The first thing that I'm noticing is that we have S, and there's an S right here, and the only unknown variable is an R, so we can solve for R by using this equation. I think that's what I'm going to do first. So I'm going to rewrite the equation, but in place of S, I'm going to write 100 pi is equal to 4 pi r squared. Divide both sides by pi, and that will cancel out the pi's. Shwink, shwink, you're gone. Divide both sides by 4, and you're left with 25. So I'm left with 25 is equal to r squared. Square root both sides, and r is equal to technically plus or minus 5, but it can't have a negative radius. So I'm going to leave it as positive 5 for the radius. And I think I have all of the things needed for v prime, but we haven't found v prime. So let's find v prime. So I'm taking the derivative now of this right-hand side. When I take the derivative, I'm still left with 4/3. So v prime is equal to, I still have that 4/3 out front. And then I have a pi as well. Now I'm going to take the derivative of r to the power of 3. So 3 comes down in front. It's going to be times 3r, and then it goes down a power, r squared. But don't forget, you have a dinner. The derivative of r is r prime. Okay, so now we have everything ready to go. Let's plug in, and then we'll find what v prime is. We have a 4/3 pi times 3. And by the way, what I should have done here is the 3 and 3 cancel each other out. So really what I'm going to do is, oh, I went too far there. I want to just erase those. Thank you. Really, I have just the 4 with no 3's. 4 pi, and then r, we just discovered was 5. So I'm going to say 5 goes here. 5 squared times r prime, and we know that r prime from over here is 0.3. So I can say times 0.3. And multiply these together. So 25 times, so sorry, 5 squared is 25. So 25 times 4 is 100. So I have 100 pi times 0.3 is 30 pi. So this is equal to 30 pi. And that means our correct answer is option E. Moving on to number 47, another related rate problem. And the radius of the circle is increasing, so that just means r prime is positive. I don't know if that's helpful. At a certain instant, the rate of the increase of the area. So some keywords here. It's a rate of the area. So I'm talking about a prime. A prime is numerically equal to, so I'm going to say is equal to the rate of increase. So I have another rate of circumference. So it's equal to, it's not 2 times, it's like literally just equal to c prime. At this instant, the radius of the circle is what? So we're asked for what is r? R is equal to our box. Okay, and you should have these speed sheet definitions memorized, but if you don't, I'm going to go ahead and read them really quickly for you. So if we remember that the area of a circle is pi r squared, then a prime, the rate of the area, is 2 pi r prime. Circumference is 2 pi r, which means circumference prime is equal to 2 pi r prime. And notice the relationship. We have a 2 pi r prime, a 2 pi r prime. The only additional thing that we have is r, which means the speed sheet definition that I'm hoping that you remember is that a prime is equal to c prime times r. And I can make that substitution. So coming back all the way back over here, this a prime, I'm swapping out this a prime for a c prime times r. Let's go ahead and write that. So I have c prime times r is equal to c prime. Divide both sides by c prime, and I'm left with r is equal to 1. Correct answer, D. Number 48. We're looking for horizontal tangent lines. So what does this mean? Horizontal tangent lines, the first thing that I'm going to note is a tangent line really just means derivative. And horizontal means that it's the slope here is 0. So if you take the derivative, it should be equal to 0. So, and the derivative really means y prime, so double interpretation. So we know that y prime is going to be equal to 0. So we're going to take the derivative of our function over here, and we're going to set y prime equal to 0 and see what happens. So here we go. Taking the derivative, that's going to be 2y prime minus 3x squared minus 30x is equal to 0. And we know that y prime is equal to 0, which means this entire term right here is going to go to 0. But I'll write it out just in case people want to see it. 2y times 0 minus 3x squared. And I'm realizing I probably should do a little bit more work here, because I can factor out a 3 and an x. So I'm going to factor out a 3 and an x, leaving me with just an x. And if I'm factoring out, technically, I'm factoring out a negative as well. So both of these negatives are being absorbed over here by this negative, which means I'm left over with a positive 10. and that's equal to 0. And just to double check that work, if I were to distribute that negative 3 back in, negative 3 times x, negative 3x squared, so far so good, negative 3x times 10, negative 30x. Okay, so it seems like I factored out correctly. So rewriting this gives me, with pen, negative 3x times x plus 10 is set equal to 0, and that happens when x is equal to 0 and when x is equal to negative 10. And I think that's an answer. Yeah, so the correct answer here is D. Moving on to 49. Okay, another related rate problem. I don't need to zoom out that far. So the area of a circular region is increasing. So if I see area increasing, that's talking about A prime. So I know that A prime is that value 96 pi. 96 pi. And increasing is a positive word, so it is a positive 96 pi. If it was decreasing, there'd be negative 96 pi. When the area is, so this is just a pure area, no A prime, just A. When the area is 64 pi, how fast in meters per second is the radius increasing? So it's asking for fast and the word increasing. Both of those indicate it's something prime, and it's going to be radius prime. So we're asked to find what is r prime. That's going to be my empty box. Okay, so I need a formula for A and A prime. Let's go ahead and get those out of the way. The formula for the area of a circle is pi r squared, and the formula for the how fast the area is increasing, this A prime, is going to be 2 pi r prime. And are either of these going to help us? Well, I know eventually I'm going to have to get r prime. That's the only r prime in here. The problem with that is I do have an A prime right here, but I don't have an r. So if I find an r, I've unlocked the problem. I can just kind of plug it all in. So we have an A, which can be plugged in here. And if I do that, then I can solve for r up here. So let's do that. I'm going to plug into that first formula. I'm going to say 64 pi is equal to pi r squared. I'm going to divide both sides by pi. Those are gone. And I'm going to take the square root, because I have r squared equals 64. So if I take the square root of r squared, that's left with r. So I can say now we have r on the right-hand side, and the square root of 64 is plus or minus 8, but it doesn't make sense to have a negative radius. So now that we have r is equal to 8, now I can plug into that second formula down here and solve. So I have A prime, which I know is 96 pi, so 96 pi. And then on the right side, I have 2 pi r, so 2 pi, and we know that r is 8, so 2 pi times 8 times r prime, which is the thing that we're trying to solve for, r prime. So, like we did before, I'm going to divide both sides by pi. Those are gone. I'm going to divide both sides by 8, and I think that's 12. 12 times 8 is 96, right? Yeah. So divide both sides by 8, and I get, I just said 12. Pay attention to yourself, Mr. Snow. So I have now 12 is equal to 2 r prime, and if I divide both sides by 2, I get r prime is equal to 6. So the correct answer here is A, 6. Number 50. We have a continuous function. I don't think that's super helpful for this problem to talk about that it's continuous, but it's nice. And then here's the cool thing. So capital F prime is equal to F. Another way of saying that is, watch this. I'm going to slap on an integral to both of these. That means that the integral of lowercase f of x is equal to, and then antiderivative and derivative over here on the left-hand side, these two symbols cancel each other out, and you're left with just capital F. So there's two ways to interpret that. I guess it's capital F of x. You can either think of it as this first definition right here, or the second definition, whichever one is most helpful. And I think the second definition is more helpful in this case. All right, so we are trying to take the antiderivative of just a lowercase f. And we know that when we take the antiderivative of lowercase f, we get a capital F. The problem here is that we have to pay tax person. You always have to check tax person whenever you're taking the integral. You have to check the inner. Okay, the inner is 2x. Is the derivative of 2x 1? No, the derivative is 2, which means you have to pay tax person. You always pay tax person when the dinner is anything other than 1. So let's get tax person set up. We need the inner, which is going to be 2x. We need the tax person, and there doesn't appear to be a tax person, so I'm just going to say 1. And then you need a u prime. U prime is going to be 2, which means I'm going to pay tax person a half. So I'm going to rewrite my integral while paying tax person. Our integral is now still the integral between 1 and 3. There's my tax person being paid, 1/2. And now I have f of 2x dx. All right, tax person has been paid. Now I have permission to take the antiderivative. And again, I'm using this fact that the antiderivative of lowercase f is capital F. So antiderivative of this lowercase f is capital F. And this is going to be equal to 1/2 of capital F of 2x. And I'm not going to say plus c. I'm going to say evaluation bar between 1 and 3. And now I'm going to plug those both in. And again, whenever you have that constant term, that 1/2 factored out, really, I'm going to leave that 1/2 really factored out throughout the entire problem. So I have 1/2, and now I'm going to do f of, okay, plugging in the 3. 3 times 2 is 6. And then capital F of, when I plug in 1, 1 times 2 is 2, so it's going to be f of 2. And there's my final answer. They might distribute that 1/2. They do distribute the 1/2. You can see that the correct answer here is E, because they distributed the 1/2 and got basically the same answer we got. All right, and on to number 51. All right, I have this integral here, and okay, when I'm thinking about this, I'm immediately thinking tax person, but I'm realizing, because I'm doing tax person in my head really quickly, that's not gonna work. So how do we do this problem? Oh, okay. We can separate the fractions. So there's this cool little trick that you can do. This is going to be equal to, I'm not going to take the integral. I'm going to keep the integral from 1 to e. But the inside, I'm going to break it up. So it's kind of this trick that if I have like 1/4 plus 2/4 is equal to 3/4. And you're like, okay, well, that's simple, Mr. Snell. What are you talking about? I'm really thinking in reverse order. I have this and I want to get 2 fractions here. So I have 1 fraction. I'm going to convert it into 2 fractions. So I'm going to first have x squared over x, and then I can subtract a 1 over x. And you'll notice that, yeah, if you do combine those like terms, this does turn into this, so that is allowed. And I'm going to put everything here in parentheses and slap on a dx here, and we're ready to take the antiderivative. If I want to simplify a little bit first, that would help me. So I can say, okay, well, I can simplify. This is still integral from 1 to e of x minus x to the power of -1, and that whole thing dx. All right, do we need to pay tax person in this case? Every single time you see an integral, you need to be thinking, do I need to pay tax person? In this case, you don't, because the only house that you have, I mean, if there was a 2 right there, then you would have a house to worry about. But the only house that you have is this powerhouse, and the inner here is x, therefore dinner is 1. Whenever dinner is 1, you don't pay tax person. All right, so just go ahead and take the antiderivative. In pen mode, please, thank you. The antiderivative of x goes up to the power of 2, then divide down by that 2. Minus, and then antiderivative of anything to the power of -1. Let me go ahead and fall into the trap on purpose. You're thinking, oh, x goes up to the power of 0 and then divide by 0. Oh, wait a sec, you can't divide by 0. And the correct way of doing that is doing natural log of that inner, which is just x. And I should be careful here because not just parentheses, it's absolute value of x. There we go. And then that is going to be evaluation bar between 1 and e. All right, so let's plug in e first. That's going to give me e squared over 2 minus natural log of e, and I can just drop the absolute value because e is already positive. So that's me plugging in e, and I'm going to subtract what happens when I plug in 1, which is going to be 1 quantity squared over 2 minus natural log of 1. All right, time to simplify. So the cool thing here, natural log of e is just 1, natural log of 1 is 0. If you don't have those memorized, you need to memorize them. At the very beginning of the year, I handed out a properties of logarithms worksheet, and you should know at least those 2 evaluations, along with some other tricks with natural logs. So e squared over 2 can't be simplified. This is e squared over 2 minus 1. And then I'm going to distribute this negative here. So this negative is going to make this term negative and this term positive. So I'm going to have a negative 1/2 and then a positive, 0. I didn't really need that. Let's go ahead and erase that. Then I can go a little bit further and say that this is going to be equal to e squared over 2. And then if I have -1 and minus another 1/2, I have -3/2. So this is going to be minus 3/2. And I think that's exactly e underneath that. That looks really, really similar. Yeah. Number 52, we've got an indefinite integral, meaning it's not definite, it doesn't have bounds. We have a lot of x's. I'm hoping tax person will be able to save us here, and it looks like it probably will. Let's try it. So tax person, we needed to declare a house, and I'm seeing this E, so I'm thinking E house. So there's our house. The inside of the house is this x to the power of 2. So if I'm setting up tax person, U is equal to that inside x to the power of 2. Tax person is out front, that's our x, and U prime is going to be, whoa, weird, equal to signs. U prime is going to be equal to 2x. So when I treat this as a fraction, this is going to be 1/2, and we can pay tax person 1/2. So it's going to be now the integral of not x, but 1/2, because we paid tax person, and it's going to be e to the power of x to the power of 2 dx. And antiderivative and derivative of e house are always fun. You just relist e house. It's going to be 1/2 e to the x to the power of 2, and don't forget your plus c. So the correct answer is, wait a sec, are a and d the same? Okay, well, I guess the answer is a and d. I'll fix that in the future. Number 53. A definite integral this time of e house. I love e house, but again, it's going to be a tax person, because if this if the inner here was just x, then we'd be cool, because the derivative of x is 1, which means you don't have to pay tax person. Anything other than that, in this case a negative 4x, you have to pay your tax person. So getting tax person set up, I'll do it up here. I think I have enough room. U is going to be negative 4x. We have our tax person. Actually, we don't see any tax person, so it must be this imaginary 1 in front of the e, right? And then that means U prime is going to be negative 4. We're going to change that 1 into a negative 1/4. Okay, so paying tax person means our integral is going to be between 0 and 1. And instead of having a 1, we have a negative 1/4 e to the negative 4x dx. All right, we've paid tax person, which means we have permission to take the antiderivative, and that's just still e house, negative 1/4 e to the negative 4x. Cool. But unfortunately here, we have a definite integral, which means instead of doing a plus c, we have an evaluation bar between 0 and 1. We need to plug in both 1 and 0. A lot of students will make the mistake of thinking they don't really need to plug in the 0, because it's typically in like polynomial type functions never been needed. This is a case where you do need it. So I'm going to have that negative 1/4. And again, whenever you have a number out front like that, I'm going to think of that number factored out of the entire thing, so I don't have to keep doing it over and over again. And I'll do that like that. So what happens when I plug in 1? When I plug in 1, it's going to be negative 4 times 1, which is negative 4, and it's just e to the negative 4. E to the negative 4. And then I subtract. What happens when I plug in 0? I get e to the power of negative 4 times 0, which is 0. Cool, there's my final answer, but I can simplify that a little bit, because e to the power of 0, that simplifies to just 1. So coming here, this is going to be, and I'll distribute that negative 1/4, since it looks like a lot of these options are distributing that 1/4 here, and well, I guess that's probably going to be the answer, but I'm gonna distribute. So I'm going to have negative 1/4 e to the negative 4, and then I'm going to subtract a 1. Oh no, I'm not going to subtract, because I have a negative times a negative, which is a positive. I'm going to say plus that 1/4, because again, I'm distributing. What's 1/4 times 1? It's 1/4. And it looks like that is going to be option D. Moving on to number 54. I have cosine of 3x. Okay, I'm always looking at the inner. I can see what house we're in. We're clearly in a trig house, or a cosine house, which means the inside of the house is 3x, and if it was just x, we'd be fine, but it's a 3x, so we have to pay tax person. So U is equal to 3x. Tax person, I don't see any tax person, so I'm going to treat this as like the 1 in front of the cosine of x. Tax person is just that 1. U prime is going to be 3, which means I'm going to pay tax person 1/3. So our new integral after paying tax person, the 1 turns into a 1/3, and we're left with cosine. Ooh, that was a bad S. I can try that again. Oh, I guess I erased the O too. Cosine of 3x dx. We've paid tax person. We have permission to take the antiderivative. So again, I'm thinking of anti-change means same. It's a same sign, so it's going to change to another positive. This is going to be positive 1/3 sine of 3x. And don't forget our plus c. Oop, I hit the button, the home button. I sometimes do that. And that looks like option C. Final answer. Moving on to 55. Yes, okay, we don't have to pay tax person for the first time, because the inside is just x. Cool. So the antiderivative of sine, anti-same is change, so it changes to a negative. This is going to be equal to a negative cosine of x, and we have an evaluation bar between 0 and pi over 4. All right, how well do we remember our trig? We're about to find out. I'm going to first plug in the pi over 4, and again, because I have that negative out front, I'm going to kind of factor that out. Negative is going to be factored out, and I'm going to have cosine of pi over 4 minus cosine of 0. All right, so evaluating these things. So pi over 4, the way that I'm thinking about this on a unit circle is I have a unit circle. Pi over 4 is right here, pi over 4. Well, I mean, technically the angle is pi over 4, but whatever. It points up to the middle in between 0 and pi over 2. And cosine is going to be the x-coordinate. This x-coordinate here is going to be the square root of 2 over 2. So when I'm doing my evaluation, this is going to be equal to, that negative is still being factored out, I have a square root of 2 over 2, and then I'm going to subtract cosine of 0. Well, cosine of 0 means I'm right here, and that distance on the unit circle is exactly 1, so I can come back here and say minus 1. All right, distributing that negative is going to give us a negative root 2 over 2 plus 1. Negative root 2 over 2 plus 1. Looks like correct answer here is D. And moving on to number 56. I have integral, another house. This time we have a power house. Those are typically easier to deal with. If the inside was x, we'd be in luck, but the inside is 3x, so we have to pay tax person again. Here we go. So we have a u is equal to 3x plus 5. And our tax person, there isn't a tax person, so I'm going to say that's that 1 right there is equal to 1. U prime is equal to 3. So I'm going to pay tax person 1/3. And before I move too much farther, there is another way to solve this one, and that's where you actually square the inside, and you never have to worry about paying the tax person. That requires you to square the first, double the product, and square the last, but I don't want to do that. I'm just going to use tax person. I think it is actually faster to use tax person. So when I pay tax person, the integral, it's not going to be 1 anymore. It's going to be 1/3. And then I have this 3x plus 5 quantity squared dx. I've paid tax person. I have permission to take the antiderivative. Antiderivative is going to be equal to, so I'll have that 1/3. And then I'm going to give some room right here before I write my parentheses because I know it's about to happen. This is going to be 3x plus 5, and that's going to go up a power from 2 to 3. And then I divide down by 3. Right here, and then plus c. So that's my final answer. I have like a 1/9 essentially. Ooh, I see 2 options have the 1/9 down here. Which one is correct? Well, it's the one that has a power of 3. So the correct answer here is number 57. All right, I've got the two things being multiplied together with an integral. I'm always crossing my fingers and hoping that tax person will save us, and I'm pretty sure it will. Let's go ahead and check. So I get to choose u to be whatever I want. I'm going to choose a more complicated thing. That's my u is on the inside. I don't want to choose something easy, so I'm going to say over here that my u is going to be x squared plus 1. That means my tax person is going to be x, and u prime is going to be 2x, and then I'm going to treat this as a fraction, which simplifies to 1/2, which is excellent. So that gets rid of that x. So this integral is now going to be, instead of x, I'm going to have 1/2 paying the tax person, and then I'm not going to write the square root, I'm going to write that as a power of 1/2 instead. So I'm going to have this x squared plus 1 to the power of 1/2 dx. The reason I'm doing that is I'm setting up for my power rules, which are a little bit easier to use. All right, I paid my tax person, I'm allowed to take the antiderivative. This is now going to be equal to 1/2, and let's just keep the inside, right? X squared plus 1, but it's going to go, I should have moved over a little bit because I have to divide down by 3/2 in a sec. This is going to go up a power, so if I'm doing 1/2 plus 1, what is 1/2 plus 1? It's the same thing as 1/2 plus 2/2, which is going to be 3/2, so it's now the power of 3/2. And then I divide down by 3/2, which is going to be 2/3, and don't forget our plus c. And again, the cool thing here, the 2's and 2's are going to cancel each other out. I guess I should actually write that out. The 2 and 2 are gone, so I should have a 1/3 out front. And there's two different answers that have 1/3, 1/3, and 1/3. Which of them is it? And I don't have any x squared anymore. That should have been gone. This is exactly what we've written after we simplify. So the correct answer here is going to be, why did I circle D? Gosh, it's going to be C. Number 58. we've got this thing. It's just a fraction. All you have to do is undo the fraction and you're ready to go. No tax person needed. So I'm going to rewrite this integral from -1 to 1 of 3 times the quantity of x to the -2 dx. And no tax person needed. I mean, we technically have a powerhouse, but the powerhouse, the inner is just x, which means dinner is 1. Whenever dinner is 1, you don't have to pay tax person. So for this one, we're going to say this is equal to 3 times, I'm going to leave some room, x to the power of, it's going to go up a power, so it's going to go up to the power of -1, and then divide down by that -1, which, I mean, I can say divide by -1, but I think a better way of saying that is just to put a negative out front like this, a -3. And I'm realizing I gave myself too much room, so I can move this, yeah, closer, like that, looks better. And then I have evaluation bar between -1 and 1. And this is not a nice form to plug into. Fractions are nicer to plug into, so I'm going to rewrite this with a fraction. This is going to be -3 over x to the power of 1, or just over x, evaluation bar between -1 and 1. When I plug those in, I'm going to get -3 over 1 minus a -3 over -1. Lots of negatives happening. Keep track of them. So the first thing I see is that that's going to turn into a plus and a plus, and I have -3 minus another 3. So this is going to be, here, let me rewrite it once to make sure that this is clear. I have a -3, and then another -3. That's going to be -6. Correct answer here is A for -6. Moving on to 59. Oh, we're getting close, guys. I feel it. We end at 64, right? All right, 59. Man, okay, so I was hoping tax person would save us. Whenever I see two things multiplied together, x times like a square root of x, if tax person can save us, I can just apply tax person and go, but tax person will not work here. So I'm just going to distribute that x and call it good, and multiply it out. That's typically the strategy if tax person doesn't work. So I'm going to rewrite this first as the integral between 0 and 1 of x times x to the power of 1/2 instead of a square root of x plus 1 dx. I'm doing it like that because I want to be able to use my power rules, rules of exponents, that's the word I'm looking for, to multiply these. So this is now going to be the integral between 0 and 1. I still haven't taken the integral. What is x to the power of 1 times x to the power of 1/2? Well, it's the same base, so you keep the base, and then you add the powers. 1 plus 1/2 is 3/2, and then I'm going to add, okay, now I'm going to distribute this x to the power of 1 into 1, which is just x to the power of 1, or simply x. And then that whole thing is going to be multiplied by dx. Okay, we don't need a tax person. I mean, yes, you're right that we have a powerhouse here, but the inner of the powerhouse is x. Therefore, the dinner here is 1. Whenever dinner is 1, you don't have to pay the tax person. So just go ahead and apply the antiderivative. This is going to be x to the power of, it's going to go up a power from 3/2 to 5/2. Divide by 5/2 is the same thing as multiplying by 2/5. So 2/5. Plus, okay, this x is going to go up to the power of 2, divide down by 2, and it's not plus c, we have a definite integral, so it's going to be an evaluation bar between 0 and 1. All right, do I have enough room over here? Maybe. We'll see if I can squeeze it in. So over here, I'm going to plug in 1. I'm going to get 2/5 times 1 to the power of 5/2 plus 1 squared over 2. And that's what happens when I plug in 1. What happens when I plug in 0? So let's subtract. When I plug in 0, I'm going to get 0 plus 0. I didn't really need to do it, but I'm going to show my work that way, just to let you know. You do want to plug in 0 just in case. I can simplify that pretty quickly. 1 to the power of anything is going to be 1. So right here, I just have 1. And 1 times 2/5 is 2/5. So I have 2/5. That was a terrible 5. My gosh. 2/5, better. Still not great. Plus 1/2. I don't have like denominators, so let's go ahead and change this. So I'm going to multiply by 2 over 2 and multiply this one by 5 over 5. And that's going to change this problem into 4/10 plus 5/10, which is 9/10. Final answer, 9/10 C. On to number 60. All right. I have a square root and a fraction, but neither of those are very scary if I can just go ahead and rewrite that. So this is going to be equal to, still the integral. I'm not taking the integral yet. I'm just rewriting. And I'm going to make it go to the top and get rid of the square root all in one step. I hope you can follow that. So 1 plus x, all to the power of, it was 1/2, but because I brought it to the top, it's now -1/2. And don't forget our dx. All right. Do we have to worry about tax person? Kind of, because we do have a house here, so we have to check the derivative of this inside. The inside is 1 plus x, but the derivative of 1 plus x is just 1. Because the derivative is 1, we do not need to pay tax person. We can go ahead and just do the antiderivative. So this is going to be 1 plus x. It's going to go up a power from from negative 1/2 to positive 1/2, and then divide down by 1/2, which is the same thing as multiplying by the reciprocal, multiplying by 2. And we have an evaluation bar between 0 and 8. Excellent. And again, when you have a power of a half, it's not great to do any plugging in. So I'm going to rewrite this as 2 times the square root of 1 plus x, evaluation bar between 0 and 8. Now it's ready to be plugged in. All right, so when I plug in, it's going to be 2 times the square root of, and really that 2 is being factored out, so I'm going to leave it like that. So keep the parentheses, 2 times 1 plus 8 minus the square root of 1 plus 0. Cool, and that's pretty easy to simplify. That's going to be 2 times the square root of 9 minus the square root of 1. Square root of 9 is 3, square root of 1 is 1, 3 minus 1 is 2, so it's going to be equal to 2 times 2, and 2 times 2 is... Number 61, we're on our last page for the packet. We have a graph, and let's mark all the points it's telling us. So at 2, 0, what's going on there? We have a horizontal tangent. Wait, 2, 0. Oh, sorry, that was a vertical tangent at 2, 0. I can read. That's a vertical tangent, which means the slope looks like that. And then at at 1, negative 1, this point, and at 3, 1, this point, we have horizontal tangents. So we'll have a tangent line that is 0, a tangent line that is 0. Oh, that was a bad line. Yeah, it didn't think it was a line. Oh, I'm just going to undo that. Try again. Good enough. For what values between negative 2 and 4, so everything, is f not differentiable? Not differentiable. And I've put that definition at the beginning of the packet, but I'm going to give it again right now. You're not differentiable for the following 3 things. 1, you have sharp corners. 2, you have vertical tangents. And it told us that we have a vertical tangent over here at 2, so that's kind of a giveaway. And then 3, any sort of discontinuities. Discontinuities. And that just means pick up your pencil, right? If you picked up your pencil, that's a discontinuity. Discontinuity. Pick up your pencil. So let's go ahead and go through this. So going so far so good, but then all of a sudden I had to pick up my pencil to come from here to here. So I picked up the pencil once. That's a point where it's not differentiable. That's okay. It's okay to be a horizontal tangent, but you cannot be a vertical tangent. That is not okay. That's in the list of things that are not differentiable. So far we have 1, 2, and so far so good. And notice that if it had included 2 and 4, then we would have had an endpoint, which would include those points as not being differentiable, but they're not included because there's no equal to signs down here. So it's just 0 and 3. So 0 and 3, which is, oh, why did I say 0 and 3? 0 and 2. I don't know why I circled 3. That's the vertical tangent, Mr. Sindel. So 0 and 2. Correct answer B. Number 62. Oh man, this is an interpretation question. I'm not the best at these. Let's try this one. Okay, so T is representing hours. So far, so good. Differentiable. Okay, so H is giving temperature. That's kind of important. And we have to interpret, what does H prime of 24 mean? So the first thing that I know is that whenever you take the derivative, that means it's changing the amount. This is like the amount of degrees, right? H is an amount of degrees. H prime is now going to be the rate of the degrees. So we need the words rate, which immediately eliminates A and B. We need the words rate, which are good. All right. And now we need to think of this thing as, well, okay, C is going to be out as well because it's not the average rate. In order to have average of anything, you need to have 1 over B minus A integral from A to B of that something, and this does not look like that. They're not even close. That's a derivative, and this is an integral, first of all. So it's definitely not going to be c. It's not going to be average of anything. So let's cross off c as well. So now it's between d and e. And the only difference between the two is one is saying the first day versus the 24th hour. And we should have the same units that we were given up here, and that kind of eliminates this one. Although you can kind of make an argument. It's kind of true, but it's not the whole first day. That would be like, you need like 1 in here instead of a 24. This is definitely the 24th hour. I would select E. Number 63. All right. We have a horizontal line, which is an asymptote. Oh, so let's put those two words together. We have a horizontal asymptote, and that is a species definition. That's the limit as x approaches positive infinity or negative infinity, which immediately crosses off all of these and gives you E. But let's go ahead and make sure that you understand what these are saying. So A is saying that the height at 0 is 2. And that's not true. An asymptote is where you approach. It's kind of like a magnet, right? As you go to the left and to the right toward like negative infinity and positive infinity, the magnet is drawing you towards a height of 2, not at 2, at that one specific spot. This is saying that it's never equal to 2, which you can kind of make an argument for, because technically asymptotes, you're not supposed to touch them, but you can, because you can have graphs that go like this, where say you have a graph, and then you can have a function that, let's say that we have maybe an asymptote right here. You can have a graph that goes and jumps through the asymptote and then gets closer and closer to it from above, but you are allowed to cross it once, so technically that does eliminate B. You are allowed to go through 2. C is saying f of 2 is undefined. Well, it's not undefined because we don't know what's happening at the x coordinate too. And we know that the y coordinate gets closer and closer to 2. It's kind of funny to put an x coordinate of 2. It's supposed to be the y coordinate of 2, y coordinate of 2, right? So that's just kind of like nonsense. D, you're saying as I get to 2, I go to infinity. What this is saying is if I had to make like a graph of what D was saying, you have some sort of, I want to use blue lines here. So you have some sort of x-axis, y-axis, and at the value at 2, it's jumping up to infinity. So you'd have some sort of graph that looked like this. You'd have like a vertical asymptote, and it would jump up and jump up, which is not what's happening here, because as we said over here, it's a horizontal line, not a vertical line. That's a vertical tangent line. So it's not D either, and the only definition that you need for E was that horizontal asymptote is limit to infinity, which you would technically use top-bottom rules for. And the final question, number 64. We have a horizontal asymptote and a vertical asymptote. What is the value of A plus C? Okay, so a horizontal asymptote, I just defined it up above, but the horizontal asymptote is whenever you take the limit, I'll write this underneath it, is the limit as x approaches infinity. So if I take that, what is the limit as x approaches infinity of that function a of x plus b all over x plus c? And to do that, you need to use your top-bottom rules, which state, look at the powers for the numerator and the denominator. The highest power for the numerator is 1. The highest power for the denominator is 1. You kind of ignore the b and the c. And whenever there's a tie, in this case, there's a tie of 1, right? Whenever there's a tie, you look at the coefficients, which is a and 1, which means our answer is going to be a over 1, or simply a. The horizontal tangent, or the horizontal asymptote, is a, and we know that the horizontal asymptote, it's set up above, is 2, which means a is 2. So you can say this implies a is equal to 2. All right, we have our value of a. Now we need our value of c, because we're doing a plus c, right? So how do we get our value of c? Well, I'm noticing immediately that c is in the denominator, and that is the definition of a vertical asymptote. And this is pulled from Algebra 2 and pre-calculus. So a VA, the definition, not in AP Calculus, just from before, is whenever you basically set the bot equal to 0. If you set the bottom equal to 0, that is your vertical asymptote. So if I set x plus c, which is the denominator, that is the bottom, if I set that equal to 0 and I solve, that means x is equal, I can write. That means x is equal to negative c. And we know that this should happen at the vertical asymptote. So I know that this x should be negative 3. So I can come down here and replace this x and say negative 3 is equal to negative c, and therefore c is equal to 3, which makes a lot of sense because check it out. If you plug in 3 right here and I have x minus 3, you would have an asymptote at -3. You always set that thing equal to 0. I'm just rewriting this again, making sense of this. If you had x minus 3 and I set this equal to 0, I would have, oh no, I would have an asymptote at positive 3, so it needs to be x plus 3. I don't know why I made that negative. Yeah, so if it's x plus 3 is equal to 0, x is equal to -3. Good. So that means c is equal to positive 3. That does make sense that it's positive and not negative. We have our value of a, we have our value of c. We're going to add those together. 3 plus 2 is 5. Correct answer here is E. Wow, and that concludes the packet. So just as some final words for you guys are probably doing this with 1 or less days to spare for the actual first final. The first final is going to be kind of rough. I think the easiest final is the third out of the 3 finals. Yeah, just good luck. Make sure that you know the speed sheet definitions like crazy. If you do have extra time, I would go back through this packet and do anything that was at all confusing. If you're like going to go above and beyond, I would print out another blank packet and see how far you can get. It's the best way to review your pretest, review self-checks, fix-ups, everything at your disposal. Just go through everything as many times as you can to get all those errors out of the way.